Hi all, welcome to goclasses. In this lecture, we will discuss GateCS AIMT3 detailed solutions. So this is GateCS All India Mock Test 3 detailed solutions part 1. Let me tell you all the Go classes AIMT solutions and all about AIMT is basically the video solution, the discussion, the advice, suggestion, tips, everything you can find in this playlist. So on YouTube, you can search Go classes AIMT. This playlist will come, and in this playlist, you will be able to find all the parts of detailed solutions. Okay, for example, AIMT, AIMT1, AIMT2, AIMT3, the solutions for all the Go classes AIMTs, the detailed solutions and all the parts, everything you will find in this playlist. Okay, the link I will provide you in the description, also in the pinned comment, also you can check it out, or you can search on the YouTube Go classes AIMT. Let me tell you, in AIMT 3 for GATE CS 2026 aspirants, in this All India Mock Test 3, more than 4,000 students they appeared live. So these are the number of live participants, more than 4,200 actually. Okay, so this is a huge number. So thank you everyone for your trust in Go classes. So keep attempting the Go classes All India Mock Tests. These are free for everyone. So you can see this is the GATE CS AIMT schedule. Every Sunday we have GATE Computer Science GATE CS All India Mock Test. Okay, so remember Sundays are for Go classes GATE CS All India Mock Test, and Saturdays are for Go classes GATE DA All India Mock Test. Okay, so every Saturday we have GATE DA AIMT, and every Sunday we have GATE CS AIMT. Okay, so don't miss any of them. Now let's start the discussion session for AIMT3 questions. Okay. So this question from computer organization and architecture, this question based on pipeline, this we have already discussed. I will provide you the link in the description in the pinned comment. This question based on cache memory, this question also we have already discussed. I will provide you the link in the description, also in the pinned comment. You can find it. Also, this question from pipeline in the COA subject, computer organization and architecture. So this question also we have done the discussion. Okay, the complete analysis of this question, the complete discussion we have already done. So I will provide you the link in the description, also in the pinned comment. You can check it. Basically, this question already we have done. Okay, and let me tell you that in this playlist also you will find the solutions of all these three previous questions. Okay, so basically on YouTube you can find this playlist, and in this playlist you will find the solution of this question, the detailed analysis, the complete analysis of this question, pipeline question, for this cache memory question, also for this pipeline question, the complete analysis you will find in this playlist. Okay, so on YouTube just search for Go classes AIMT, or you can find the link in the description, also in the pinned comment. Okay, so let's move on now. Let's solve this question from cache memory in computer organization and architecture subject. So the question is saying that consider a 4096 byte direct mapped cache with 16 byte blocks. So the block size, the line size, that is 16 byte, 256 blocks. So this is a cache memory, and in this cache memory you can see, consider 4096 byte direct mapped cache. So this is the cache memory size. The size of cache memory, that is 4096 byte. Okay, and this is a cache memory with 16 byte blocks. This is the line size, and 256 blocks, this is the number of lines in the cache memory. Okay, remember this 256 blocks, this is not the number of blocks in the main memory. This is the number of blocks in the cache memory, or I can say this is the number of lines in the cache memory. Okay, because this first statement, this is about the direct mapped cache. Okay, here you have the information about the direct mapped cache, that the size of this direct mapped cache, that is 4096 byte, and the size of line, the line size, that is 16 byte, and you have 256 lines in the cache memory. Initially all the blocks are invalid, means initially you can assume that the cache memory is empty. Okay, next you can see the physical address size, that is 32 bits. This is the physical address size, or I can say main memory address size. Suppose the following sequence of memory addresses are accessed. So you can see this sequence of memory addresses we are accessing. The question is saying how many of these memory accesses will result in a cache miss. Okay, so this is actually a very standard and very easy question. What we need to do? First, we need to find the physical address division. You can see we have direct mapped cache. In a direct mapped cache, we can divide the physical address into three parts. So you can see we have direct mapped cache. In a direct mapped cache, the physical address I can divide into three parts. I can divide. So this is overall this entire address. This is basically your physical address. So the size of physical address, that is 32 bits. So you can see 32 bits. This is the physical address. Okay, 32 bits physical address. And you can see we can split this address into three parts. This least significant part, that will be your block offset, or you can say byte offset, or you can call it word offset. So you can see this is basically block offset. Okay, and you can see the middle part, this is your index, or I can say line index. Okay, for direct mapped cache, this index will be line index. And this most significant part, that will be the tag. Okay, so very simple. Now you can see what will be the number of bits required for block offset. You can see that we have 16 byte blocks. Okay, so 16 byte blocks. From here you can see that block offset bits, what that will be, how many bits are required for block offset. So that will be 4 bits, yes or no? Okay, because within a block total you have 16 byte. Within this block, within any particular block, you have total 16 bytes. So to identify one byte, to identify a particular byte within this block, how many bits we need? So that is 4 bits. Okay, this is the block offset. Very simple. So I can say that 4 bits we require here. Next, you can see what about this line index, how many bits we require for line index. This line index, it will indicate the line number. Okay, so how many lines you have in the cache memory? You can see we have total 256 lines in the cache memory. Okay, so you can see that total we have 256 lines in the cache memory. And from these 256 lines in the cache memory, if I want to identify a particular line, then how many bits we need? So to identify a particular line, or I can say for the line index, how many bits we need? That will be 8 bits. Okay, so you can see here we need total 8 bits. And what about tag? So the remaining bits will be required for tag. So you can see 32 minus 8 minus 4. So 32 minus 12, that will be basically 20 bits. So 20 bits we need for tag. Very simple. Okay. Now you can notice that all these addresses, all these memory addresses that are given to you, remember these are not the block addresses. These are the byte addresses. These are the main memory addresses. And by default, the main memory is byte addressable. So at every address, you will find a byte. Or I can say in the main memory, for every byte, we have an address. Okay, so please understand that these are not block addresses. Okay, these are the main memory addresses, means these are the byte addresses. Okay, so remember these are not block numbers. These are not block numbers. Okay, these are not block addresses. These are not block addresses. Okay, these are actually what? These are actually byte addresses. Okay, yes or no? Or I can say main memory addresses. Byte addresses in main memory. Because by default the main memory is byte addressable, so at every address you will find a byte, or I can say in the main memory for every byte there is an address. So you can see that this is basically your main memory address. These are basically main memory addresses. Okay, you can see these main memory addresses, these are written in hexadecimal. This 0x, this indicates hexadecimal notation. Okay, this indicates hexadecimal number system notation. So in the hexadecimal number system, in the hexadecimal notation, these addresses we have written. And remember how to convert any hexadecimal number, any hexadecimal notation number. If I want to convert into binary, then what I need to do? Very simple. Every hexadecimal digit corresponds to a 4-bit binary number. Yes or no? Okay, so very simple. Every hexadecimal digit basically corresponds to 4-bit binary number. Okay, is this point clear? So here you can notice one thing, that The least significant 4 bits, these are basically block offset in the address. So if you have any address, okay, example, let me take one example. Consider this address like 0x0567, okay, 0x0567. Now notice one thing, that this 0x, this is just a representation for hexadecimal notation. Okay, so this simply indicates hexadecimal notation, nothing else. Okay, so this simply indicates hexadecimal notation. Hexadecimal notation. Okay, so here I can say that these are hexadecimal digits. Okay, so this is basically hex digit. I can say this is basically hex digit. So if I want to convert this to binary, then what I will get, you can see binary. In binary, what I will get, notice one thing, that address size is actually 32 bits. Okay, so please understand, actually this address is like this, because in 32 bits, what this address will be, you can see in 32 bits, because remember the main memory address size, that is actually 32 bits. So remember, actually this address is like this, 0x, and these these are 0 0, basically most significant hexadecimal digits. These are basically 0 0 and so on. Okay, you can see total how many hexadecimal digits we need for 32 bits. For 32 bits, you can see we need 32 divided by 4. Okay, so basically 8 hexadecimal digits you need, because one hexadecimal digit corresponds to 4-bit binary number. Okay, so you can see total we want basically 8. Okay, so you can see it will be like 0 0, then you can see 0567. Okay, this is your basically address. Okay, and of course this address, if you convert to binary, then what will happen, then it will be like all zeros. Then you can see here this 5, what it will be, you can see that basically it will be like, okay, 40. Okay, because of this 0 40, then because of the next 5, because of this 5 you will say 01 01, because of this 6 you will say 0110, and because of this 7 you will say 0111. Okay, so this will be your binary. I hope you understood this. Okay, very simple. So very simple point. Now you notice one thing, that the least significant 4 bits, these are for block offset. So in this address also, this is basically block offset. Okay, you can see this is actually block offset in this address. In the hexadecimal, the address, in this hexadecimal address, I can say that this least significant one hexadecimal digit, least significant one hexadecimal digit, that is your block offset. And then you can see next 8 bits, these are line index, means these next two hexadecimal digits, this is your line index. Okay, is this clear? So remember, this is actually our line number. This is the line number, I can say. This is the line number. I hope you understood this point. Okay, so very simple. So this is the idea, that the least significant 4 bits in the 32-bit address, the least significant 4 bits, these are block offset. So if I write this physical address in hexadecimal notation, then I can say that least significant one hexadecimal digit, that is your block offset. Then next two hexadecimal digits, those will be line index, and the remaining most significant hexadecimal digits, these will be tag. Okay, I hope you understood this point. So this simple thing we have to understand. And now let me tell you one thing, that when addresses, main memory addresses are given to you, then to which line they will map to, because this is a direct mapped cache. In a direct mapped cache, what happens, in a direct mapped cache, every main memory block maps to a unique line. And remember, every main memory address is contained in a unique main memory block. So whatever main memory address you take, that belongs to a unique main memory block. This main memory block will map to a unique line. So I can say that this main memory address, it will map to a unique line. Okay, is this point clear? And to which line any main memory address will map to, that will be found, that will be told by this, that will be indicated by this line index. Yes or no? So means if the address is if the address is given in the hexadecimal notation, then in this hexadecimal notation address, remember this least significant hexadecimal digit, you forget about it because this is block offset. The next two hexadecimal digits, that will be your line number. I hope this point is clear. Okay, and remember we only care about tag comma line number. Okay, basically the line number will tell you to which line this address will map to. Okay, to which line the block containing this address will map to, because remember from the main memory, when we fetch a address, this address, when we fetch to the cache memory, then we don't fetch only this address, we fetch the entire block containing this address. Okay, is this clear? So very simple point, that this index, I can say this index will tell you to which line number the block containing this address will map to. Okay, and also this tag will tell you what this tag will tell you. This tag will tell you that in this line, let's assume this is a particular line, then in this line, among all the candidate blocks that can map to here, okay, among all the main memory blocks that can possibly map to here, among them, which is actually present right now. Okay, so that will be told by the tag. I hope you understood this point. So now we can very easily solve this question. So let's solve it here. You can see, because this is a direct mapped cache. So in a direct mapped cache, what happens? Let me quickly write it here. So if you have a main memory address, let's assume this is a main memory address. This is main memory address. Okay, this main memory address, this belongs to a unique, this belongs to a unique block. Okay, this is main memory block. This is main memory block. Okay, and in a direct mapped cache, this main memory block, it maps to a unique line. Maps to unique line in cache. Okay, so overall the same thing I can say for this main memory address also, that this will also map to unique line in the cache. Okay, very simple, that's it. So now let's solve this question. So when we want to access this address, remember initially the cache memory is empty. Initially all the cache lines, these are basically invalid. So initially the cache memory is empty. Now tell me, to which line number this address will map to? To which line number the block containing this address will map to? So let me know. Already we know that. Notice one thing, all these addresses, these are given in the hexadecimal notation, and in all these addresses basically only 4 hexadecimal digits are given to you. So the remaining most significant hexadecimal digits, these are basically 0000. Yes or no? And we already know that if you have this address like this, for example, if you have 0x, if you have main memory address, let me write it here. If you have main memory address, if you have main memory address like 0x, then let's assume something PQRS. Okay, PQRS. Now here remember, this QR, this is your line index. Okay, this will tell you about the line number. And this P, this is your tag. Okay, and this is irrelevant for this question. Okay, this block offset, this is irrelevant for this question. We don't care about, irrelevant for this question, not relevant for this question. Okay, very simple. I hope you understood. So let's see this address, it will map to which line? So you can see that this 5 6. Okay, yes or no? Everything, let me write in the hexadecimal. Everything I'm writing in the hexadecimal. Okay, the complete analysis we will do in the hexadecimal notation. So you can see this will go to where? This will go to line 5 6 in the hexadecimal, of course, in the hexadecimal. Okay, so let me create this main memory, this cache memory architect. I can say this template. Okay, so outlet or whatever this is called. So let me create this cache memory template here. So you can see there is a line 5 6. Let's assume this is line 5 6. Okay, so here in this line you can see I will put this tag. Okay, the tag is 0. Is this clear? Is this clear? This is basically tag. I am putting this tag here. This 0, this is basically your tag. So I can say that it simply means that in this line, in this line 5 6 in the hexadecimal, in this line we have this block 0. Okay, is this clear? Let me know. Actually the block number is actually this whole thing. Okay, let me write this point also, that block number, let me tell you, the block number if you want to find, or the block address if you want to find, block address, this is basically tag plus index. Okay, is this point clear? This is basically tag plus index. So please understand that block address, that is basically tag plus index, means in this address you have this block offset, this is your block offset. Okay, and the remaining part, this is your block address or block number. Okay, this is your block address or block number, and this block address has two parts, one is tag, another is index. Okay, if you have direct mapped cache, then index means line index. If you have set associative cache, then index means set index. And if you have fully associative cache, then this index will be invisible, or I can say basically non-existent. I can say that in the fully associative cache we don't have any index field. Okay, yeah, I can say that in the fully associative cache this block address will be basically tag. Okay, very simple. So here I can say that this 0, this tag I will put here. Okay, is this point clear? Of course I should not say that this 0 indicates block 0. No, this 0 does not indicate block 0, because block number is basically 056. Okay, that is the block number, because I told you that block number is basically tag plus index. Okay, so this tag plus index, this is your block number. Okay, very simple. Now let's see quickly. So here I can say that this will be a miss, yes or no. So let me write here M, that this is a miss. What next? What about the next? You can see this next address, this address when we access, then it will map to which line? It will map to 3C. Okay, this will map to 3C. Okay, so this is line 3C. So to this line it will map to. So definitely this is also a miss, and this tag I will put here 0. Okay, is this clear? Very simple. Now let's see the next address. This next address, it will map to which cache line? So you can see it will map to 8B. Yes or no? 8B. So it will map to 8B. It will map to 8B. Okay, so you can see here it will map to. So definitely this is also a miss. Now you can see this tag I will put here 1. Okay, now let's see the next. You can see this will map to which cache line? This will map to 87. Yes or no? Okay, so there is 87. Let's assume this is 87. Okay, so here it will map to 87. This address will map to line number 87 in the hexadecimal, and this tag I will put here 0. Okay, so yes, this is also a miss. Now let's see the next. You can see this next address, it will map to where? It will map to line 87. Okay, yes or no? Line 87 in the hexadecimal. So this will also map to this. But now we need to check. Now we need to check that in this line, the block that is present, is it the same block? Tell me, in this line, the block that is already present. So tell me, is it the same block? Yes, it is the same block. Yes or no? Because the tag is telling you. You can see this address will actually map to this line number 87. Okay, and you can see the tag is also 0. The tag is 0. So yes, this is actually a hit. Okay, basically it means that these two are 2 bytes of the same block. Okay, is this clear? These are basically 2 bytes of same block, of same memory block. I hope this point is clear. Okay, these are the 2 bytes of the same memory block. And what are the memory block? What are the memory block? The memory block is basically 087 in the hexadecimal. In the hexadecimal. I hope you understood this point. So very simple. Now let's see the next. Notice one thing. Here the block offset is different. Okay, notice the block offset here is 3. Here it is C. So it simply means that these are 2 different bytes of the same memory block. Because you can see this least significant hexadecimal digit that indicates the block offset. Yes or no? So I can say that these 2 addresses, these are basically 2 different bytes in the same memory block. Very simple. So this is a hit. What about the next? again you have 87. So this address will map to line 87. Now you tell me, already in the line 87 we have a block. So tell me, this address, does it belong to the same block? Yes, it belongs to the same block because you can check the tag. Okay, yes or no? You can check the tag. The tag is also 0. Yes, tag is 0. So this is also a hit. So please understand that these are basically, here I can say this also. Okay, you can say these are basically 3 bytes. Okay, all these are basically 3 bytes of the same block. I hope you understood. Now let's see the next. You can see this next, where it will go, it to which line it will map to. It will map to 8e. Yes or no? It will map to 8e. To this line it will map to. So yes, this is a miss. Okay, and this tag I can put here. This tag, let me put here 1. Very simple. Now let's see the next. That is, this address, it will map to which line? It will map to 87. Now in this 87 already a block is present. So tell me, this address, is it present? Does it belong to this block? See, this address will map to line 87 in the hexadecimal. Now already a block is present in this line. So does this address belong to that block? The answer is no, because notice here the tag is 1, but this tag that we are storing, that is 0. So definitely I can say this is actually a miss. Okay, but notice one thing. This is a miss. So what I will do? You can see in the direct mapped case, any main memory address will map to a unique line. So remember, this address will definitely map to this line. So I can say that when we are accessing this address, then what we will do? The block containing this block we will fetch in this line. Okay, yes or no? So now this tag I can change to 1. I hope you understood this point. Okay, now let's see the next. The next you can see, that is 8b, means this address will map to line 8b. Okay, in the 8b, in this line 8b already there is a block. So we have to check, does this address belong to the same block? So yes, because you can see the tag is basically 1. Okay, the tag is actually 1. So this is actually a hit. Okay, very simple. Now what next? You can see this next address, it will map to which line? It will map to line 7a. 7a will be somewhere here. Okay, so let me just make another. So you can see this is line 7a. Let's assume this is line 7a. 7a. Okay, this is the line 7a. So you can see that this address will map to line 7a, and this line 7a, that is already empty. So yes, this will be a miss. Okay, and this tag we will put here. Okay, is this clear? Very simple. I hope you understood. Now let's see the next. This address, it will map to line 87. Yes or no? It will map to line 87. Is there any? Yes, this is the line 87. Okay, so you can see in the line 87 already we have a block. So we have to check this address, does it belong to that block? Okay, so you just check the tag. So you can see here the tag is 0. But now here in this line 87 the tag is 1. So yes, this is actually a miss. Okay, and now this tag we will replace by 0. Is this clear? Very simple. Now let's see the next. This will map to line 56. Okay, so this is the line 56. So this address will map to line 56. Now already there is a block present in the line 56. So you ask, this address, does it belong to that block? So you can see the tag, you will check, the tag is 0. Yes, the tag is 0. The tag is matching. So yes, this is actually a hit. Okay, what about the next address? You can see it will map to line 8e. In the line 8e already there is a block present. So you have to check whether this address belongs to that block or not. So you can see, you will check the tag. The tag is 1. Yes, the tag is 1. So yes, this is also a hit. Okay, very simple. Next, you can see this will map to line 14. The line 14 is basically here. Let's assume this is line 14. So you can see that this address will map to line 14 and the tag is basically 0. This tag I can put here. Next, you can see this address will map to line 2c. Okay, line 2c. So line 2c will be, let's assume, here. Okay, this 2c line is here. So I can say that this address will map to line 2C. 2C, that is basically empty. Okay, this line is empty. So this will be a miss. Okay, this will be a miss. And here I will put this tag 0. Okay, what about this? If this was a hit or a miss? This 1 4, this was also a miss. Okay, next, let's see this. This address will map to which line? This address will map to line 2C. In this line 2C already there is a block, so you have to check whether this address belongs to that block or not. So you will match the tag. You can see the tag is basically 0. Yes, that is tag is matching. So yes, this is actually a hit. So finally, you can see total number of misses. What is that? You can calculate 1, 2, 3, 4, then 5, 6, then 7, 8, then 9, 10. Okay, you can see the number of misses, that is basically 10. I hope you understood the complete analysis of this question. Okay, very simple question. So did you solve this in the AIMT? Let me know during the test. Were you able to solve it? Very easy question. I hope you understood the complete analysis of this cache memory question. This is a standard question. This type of question has already come in the GATE exam, and many times this type of questions they come in the GATE exam from the cache memory. So this is a very standard and frequent type of question. So I hope you solved it correctly. If you did not solve it correctly, then I hope you understood the complete analysis that we have seen just now. Okay. Let's solve this question based on magnetic disk. So the question is asking, a computer scientist needs to evaluate the performance of his computer in order to calculate the response time of an algorithm. Considering that all the sectors of track 0 are read starting from sector 0, and then all the sectors of track 1 starting from sector 0, and so on. The rotational latency is 30 millisecond. This is the rotational latency, means one rotation time. Okay, your disk is rotating, so one complete rotation it will take 30 millisecond. A seek takes 20 millisecond between adjacent cylinders and 80 millisecond in the worst case. Means if you are going between adjacent cylinders, if the read write head, in the disk we have a read write head, if that is moving between adjacent cylinders, then the seek will take 20 millisecond, and in the worst case it will take 80 millisecond. Switching between tracks within the same cylinder can be done simultaneously. In the same cylinder, okay, let's assume this is a cylinder. So you can see in the same cylinder, this is a track. Now this is the track, this is the track. So switching between these tracks in the same cylinder, if you are switching between these tracks, then that can be done. That can be done, you can see, instantaneously, means immediately it can be done. There is no delay. Okay, so you can see that the switching between tracks within the same cylinder can be done instantaneously, means immediately without any delay. In this way, how much time is required to read a disk, the complete disk I want to read? Okay, so we want to read a disk with 2400 cylinders. This is the number of cylinders, and you can see each cylinder has total 6 tracks of 32 sectors, and the answer must be in the seconds. So this is a really beautiful question. I have taken this question as it is from a top university, and let's solve this question now. But before we solve this question, actually let me address some confusion in this question. Some students were getting confused why we did not consider the average rotational latency. Okay, also some students were getting confused why we included this this worst case seek time also. Okay, so let me tell you, in this question you can notice, actually in this question it is not clear that what is the initial position of the read write head. I think that information should have been given. If that information was given, then I think this question would become very well framed question. But let me tell you, in this question I did not add extra line. What was the reason? Because this is a question from a top university, so I did not want to change it. Okay, Because sometimes in the gate exam also it happens that sometimes in the gate exam you have to read question maker's mind. It happens sometimes. Okay, so this is one reason, because this question is taken from a top university, so I did not change this question as it is. I have taken this question. Okay, but let me tell you my opinion that in this question this information should have been given, that initially what is the position of read write head. Okay, so this should be given in this question, I think. Now let me tell you, if this information is given, let's assume, okay, for a moment, let's assume this information is given that initially, assume, for a moment, assume, let's assume that in this question, I give you that initially read write head of the disk is at, is at, let's assume, initially it is at cylinder, the last cylinder. You can see total we have 2400 cylinder, and the cylinder number is starting from 0. So let's assume is at last cylinder. Okay, it is at last cylinder. Last cylinder means basically 2399th cylinder. Okay, let's assume this information is given to you. Now, if this information is given to you, then you can easily see that first we have to go to track 0, means first initially first we have to go to cylinder 0. Yes or no? So from this last cylinder, if I want to go to cylinder 0, then definitely this worst case seek I need to take. Yes or no? This 80 millisecond I need to take. This is one thing. This assumption, if this is given in the question, then it will be a very good assumption. Okay, the question will become very well framed. Okay, and one more thing that initially read write head, initially read write head at sector 0. Okay, means basically if initially the read write head, if that is already at the sector 0, means at the starting of the sector 0. Okay, in that case we don't have to consider the average rotational latency. Yes or no? Do you agree with me? So if this assumption is given in the question, then it will become a perfect question. But still, I did not make these assumptions. I did not give you these assumptions, these extra statements in this question. I did not give because I did not want to change this question. And there are two reasons for that. The first reason is that whatever assumption you make, these options that you can see, these are actually very, very, very far away from each other. Okay, this is the one reason. Are you getting my point? You can see the options are very far from each other. Look at the options. These are very far from each other. So whatever assumption you make about the initial position of the read write head, whatever assumption you make, remember these options, these are very far from each other. So definitely you will arrive at the correct answer. Okay, so I don't think that you can say that because I did not know the initial position of the read write head, so that is the reason I could not solve this question. No, that is a wrong. That is a wrong. This is basically excuse. Okay, because remember you can see the options; these are actually very far from each other. So whatever assumption you take about the initial position of the read write head, you can arrive at the approximate answer. I hope you understood this point. This is the one reason. The second reason, let me tell you. You can see the question is giving this information that 80 millisecond in the worst case. So one thing is certain, the question maker was thinking that initially the read write head, this is not on the cylinder 0. Yes or no? Because if initially the read write head is at the cylinder 0, then there is no need of this worst case seek. Do you agree with me? Okay, let me tell you, in the disk, which is cylinder 0, which is cylinder, which is the last cylinder, and which is the first cylinder. Can anyone tell me? See, if you have this spindle is there, okay, this spindle is there, then you can see we have cylinders. Okay, so let's assume this is a cylinder. Okay, this is another cylinder. Sorry, this is a cylinder. Okay, and you can see basically you can see this is a cylinder. It's like this. This is a cylinder. Then this is a cylinder like this. Okay, then this is a cylinder. Okay, so you tell me like this. Let me know which is cylinder 0 and which is the last cylinder. What do you think? So let me tell you, this is the cylinder 0. Okay, is this clear? This is the cylinder 0 by default. This is the cylinder 0, means the outermost cylinder, that is your cylinder 0. I hope this point is clear. So remember, the cylinder 0 is basically the outermost cylinder. This we have seen in our magnetic disk lectures. Okay, if you have watched. So you can see this is the outermost cylinder. I can say that this is the outermost track. Okay, is this clear? And you can see this is actually your innermost cylinder. This is the innermost cylinder. This is your, you can see this is your 2399th cylinder. 2399th cylinder. Okay, 2399th cylinder. Is this point clear? I hope you understood. So please understand that this is the by default assumption. This is the by default thing in the disk, in the magnetic disk. When we address the sectors, okay, there is a topic in the magnetic disk how to give the address, how to assign the address, okay, to the sectors of the disk. So you can see in that addressing, basically in the disk addressing, this is the assumption that we make. Okay, this is part of disk addressing. So in the disk addressing, this is the assumption that we make, that outermost cylinder, this is cylinder 0, and you can see this innermost cylinder, this is your cylinder 2399. Now you notice one thing. If the examiner is thinking that initially the read write head is at the cylinder 0, means at the outermost cylinder, then you can notice that there is no need of worst case seek, because you can see from here I will go to the adjacent cylinder, from here I will go to the adjacent cylinder, like that. Yes or no? And you can see the seek takes 20 milliseconds between adjacent cylinders. So one thing you notice, because because of this given information, what the question maker was thinking, what the question maker thinking, the question maker must be thinking that initially the read write head is at a arbitrary place. Yes or no? So the question maker thinking that initially read write head is at an arbitrary cylinder. We don't know at which cylinder, at an arbitrary cylinder. Okay, is this point clear? Let me know. So this is what the question maker must be thinking. If this question maker has given this information, then the question maker must be thinking that initially the read write head is at the arbitrary cylinder. And you can notice one thing here. What about the average rotational latency? Should we consider that? Means, should we consider that to bring this sector 0 of the track 0 under the read write head, should we rotate the disk, or is it already available under the read write head? Very simple question I'm asking. What do you think from this question, from the language of this question? What do you think that initially the read write head, is it already present at the starting of the sector 0? Is it already present at the perfect place, or is it, or should we rotate the disk so that the sector 0 starting point can come under the read write head? What should we assume here from this question, from the language of this question? You can see from this question, from the language of this question, I think that the question maker is thinking that the read write head, it is already available at the perfect position, means the starting position of the sector 0. I think this is what the question maker is thinking. Okay, but again I am telling you that it should be given in the question. Okay, so maybe I will change this question, and one extra line I will add in this question. Basically this line I will add in this question, that initially the read write head is at the cylinder, at the last cylinder, and initially the read write head is at the sector 0. If I mention this information in the question, then definitely you can solve this question very easily. Okay, and I will add this information in this question, don't worry. Okay, but I'm just telling you that this question I've taken from a standard university, and they gave this question as it is with no extra information. So that is the reason I also did not add extra information. But from this question language, you can read the question maker's mind. you can read the question maker's mind that if this information is given that the worst case seek is 80 millisecond, it must be, in question maker's mind that the read write head initially is at a random, or I can say arbitrary cylinder. Okay, so first we have to bring the read write head on the cylinder 0. Yes or no? So for that, this 80 millisecond seek we need to take. Okay, we need to spend. So very simple. And what about the average rotational latency? So for that, I think this should be given in the question. Okay, because one more thing you notice, if you are taking this 80 millisecond in the worst case, okay, means if the question maker is thinking that initially the read write head it is already available on a random, or I can say arbitrary cylinder. If this is what the question maker is thinking, then of course, if you bring this read write head on the cylinder 0, it will take 80 millisecond seek, it will take. But also notice one thing. Now, of course, we cannot assume that our read write head will be at the starting of the sector 0. Yes or no? This we cannot assume. Do you agree with me? So overall, I think that this question should have this extra information, and this extra information I will add in this question. Okay, but I'm just telling you that whatever assumption you make, with any assumption, these options are already far away from each other. So definitely you will arrive at the correct answer if you solve this question. Okay, this is one thing that I wanted to tell you. Okay, but I hope this has removed all your confusion, because under this question there were many comments. Students were asking, sir, why are we taking this 80 millisecond worst case seek? Okay, sir, why are we not considering the average rotational latency? Why are we assuming that the read write head is already available at the starting of the sector 0? Why are we assuming that the read write head is initially at an arbitrary cylinder? So basically these type of questions, these type of doubts many students were asking. So I hope I have answered your doubt. Overall, the conclusion, let me tell you, the conclusion is that this information should be given in the question. Okay, with this information, now we are going to solve this question. Is this clear? So you can see this is the assumption. This information, let's assume that initially the read write head, this is at the last cylinder, okay, or arbitrary cylinder, but the read write head, this is at the starting of the sector 0. So basically, because your read write head is already available at the starting of the sector 0, so it means that we don't need to consider the average latency, average rotational latency, that we don't have to consider, but we have to consider the worst case seek. Okay, I hope you understood this. Now let's solve this question. Now it is a very easy question, but before we solve this question, let me quickly tell you, let me quickly revise this magnetic disk. Basically, in the disk, you can see that we have some we have some cylinders. You can see this is a cylinder. Okay, then this is a cylinder. So basically, you can see we have some platters. These are the platters. For example, in this diagram, you can see there are 3 platters. Every platter has 2 surfaces. Okay, this surface and this surface, this surface, this surface. Okay, every platter has 2 surfaces. Now you can see every surface, if you notice, okay, look at every surface, that every surface is basically divided into these tracks which have the same center. Okay, so you can see that we are dividing this every surface, basically we are dividing in tracks, and these tracks, these are basically uh, these are, I can say, all these tracks of the same radius, they create a cylinder. Okay, very simple. I hope you understood this point. And like this, so very simple, this is the architecture of disk, magnetic disk. Okay, very simple. And you can see these are the read write head. Okay, so every surface has a read write head. You can see this surface has a read write head, this surface has a read write head. So every surface has a read write head. You can notice. Okay, you can see every surface has read write head. Okay, and this disk, this rotates. Okay, so this is the rotation. So this is a spindle. In between, you can see this handle. This is called a spindle, and this disk rotates. Okay, very simple. Now every track is divided into sectors. You can see that every track, if you look at this, for example, this is a sector, this is a sector, this is a sector. So every track is divided into sectors. Okay, and you can see all the tracks with the same radius, they form a cylinder. Okay, so cylinder means basically in all the surfaces, the tracks with the same radius, they will create a cylinder. Okay, they will form a cylinder. Okay, and we have platter. Every platter has two surface, and every surface is divided into tracks, and these tracks, they have the same center. Okay, means they are basically concentric, right? This is the word. The tracks have the same center like this. Okay, they have the same center. So I think this is the word. What is the word? Concentric, something like that. Okay, so anyway, I hope you understood. This is the structure of the disk, and let me quickly tell you. You can see some by default things. Let me quickly tell you. You can see by default the track numbers, they will start from 0, and the track 0 is the outermost track. The cylinder 0 is the outermost cylinder. The highest number track, this is next to the spindle. Okay, means the innermost track, this is basically the highest numbered track. The innermost cylinder, this is the highest numbered cylinder. Okay, next you can see, when can I say two sectors are close? So notice, when can I say two sectors are closest? Two sectors will be closest if they are on the same track. Yes or no? If they are on the same track, then those two sectors will be closest. Now, if they are not on the same track, then what can we say when the two sectors will be close? Then you can see this is the decreasing order of closeness. So if two sectors are on the same track, they will be close. You can see the two sectors will be very close if they are on the same block. Then if they are on the same track, if they are not on the same track, then if they are on the same cylinder, if they are not on the same cylinder, then they are on the adjacent cylinder, and so on. This is the closeness of sectors. Okay, all these concepts we have seen in our go classes magnetic disk lectures. Okay, you can see this also another concept. Two records on the same sector are obviously very close to each other. Okay, so you can see are obviously close together as possible. You can see because this sector, remember, sector is the minimum unit that we read or write. Yes or no? In the disk, this sector is the minimum unit that we read or write. So you can see that if two records are present on the same sector, then obviously they are as close as together possible. You can see because they are read or written as part of the same sector. Next, you can notice when the platter will spin, when your platters will spin, or I can say when the disk will spin, then other sectors of the same track will also will we will also read them or write them. Okay, when as the disk is rotating. Okay, means when they will rotate under the read write head. Now you can see that in a complete rotation, in one complete rotation, the entire track we can read. Yes or no? Very simple. So you can see that in the current disk design, all the data on a track we can read or we can write in one rotation. Very simple. And you can see after a track is read or written, then what we will do? Then we will read or write the track in the same cylinder, the next track in the same cylinder. So you can see that another disk head becomes active, and another track in the same cylinder we will read or write. Now, when a cylinder is complete, when the entire cylinder you have read, then you will go to adjacent cylinder. So you can see, you can read this, that this process will continue until all the tracks of the current cylinder we will read or write. Okay, so first we will read the entire cylinder, and then we will go to the adjacent cylinder. So you can see that then the arm assembly, means the read write, the this read write head, this will move to the adjacent cylinder. Okay, very simple. I hope you understood this point. Okay, so you can just read this paragraph. Okay, every information is written here. All these concepts we have already discussed in our magnetic disk lecture, but let's see this. You can see the data on a disk is ordered by the following way, means how the data is stored on the disk. So let's see this quickly. You can see first we store it on the first sector of the first surface of the first cylinder. See, very nice, beautiful line here. How the data we store on the disk. You can see it is first stored on the first sector of the first surface of the first cylinder. Okay, then in the next sector, then in the next sector, until all the sectors of the first track are exhausted. Then we move to the first sector of the second surface, but we will remain on the same cylinder. Okay, on the same cylinder, we will move to the next surface. Then you can see, then the next sector and so on. Now, once it will exhaust, it exhausts all the available surfaces. Like this, we will go surface by surface in the same cylinder. Now, once the first cylinder is exhausted, then we will move to the adjacent cylinder. The next cylinder, to the next cylinder we will move. Okay, this is the concept. I hope you understood. Now you can easily solve this question. So let's solve it. You can see initially we are assuming that we are at arbitrary cylinder. So what are the step number one? Tell me. Let's see the steps to solve this question. You can see that initially assume, or assume that this is given in the question. Let's assume this, that in the question this information is given, that initially the read write head is at arbitrary cylinder. Okay, so let's assume this initially. Now tell me, what will be the step number one? What do you think? The step number one will be, we will bring this read write head on the cylinder 0. Yes or no? Okay, yes or no? So we will bring this read write head on cylinder 0. This is the step number one. On cylinder 0 we will bring. Okay, how much time it will take? From arbitrary cylinder, the read write head we want to bring to the cylinder 0. Then how much time it will take? That is your 80 millisecond worst case. This is given in this question. So 80 millisecond time already gone. Okay, yes or no? Very simple. I hope you understood. Now, what are the step number two? What are the step number two? After this, now already we are assuming, assume that it is given. Okay, for a moment, assume that it is given in the question, because as I told you that in this question, one line should be given, one extra line should be given in this question, that initially the read write head is at arbitrary cylinder. Also, also remember, initially basically the read write head, this is at the starting of the sector 0. So you don't have to worry about the average rotational latency. So basically just assume that the read write head is initially placed at starting of sector 0. Okay, so no need to, so I can say that there is no need to bring this sector 0 under the read write head. Okay, yes or no? So there is no average rotational latency considered. Okay, so very simple. Now you can easily solve this question, because now we are at the sector 0 of the cylinder 0. Yes or no? Of the in the cylinder 0, in the track 0, we are at the sector 0. Okay, so I can say that now we are at, where we are at, we are at cylinder 0, track 0, sector 0. Okay, so we are here. I hope you understood this point. Okay, so now very easily you can solve. Notice one thing, that entire track you can read in one rotation. So already you can see that for one track how much time it will take. Means you can see one track, for one track how much time it will take. One track, the entire track I can read in one rotation. Yes or no? In one rotation the entire track I can read, and one rotation time, that is your 30 milliseconds. So one track will take 30 millisecond time. Yes or no? Okay, now notice one thing, as soon as I read this track, then I will go to the next track. Yes or no? And in the question it is given that we have 6 tracks. Every cylinder has 6 tracks. Okay, every cylinder has 6 tracks. So you can notice that one track will take 30 millisecond, because in one rotation one track we will read. Okay, and now you can see that per cylinder we have 6 tracks. Okay, so you can see one cylinder will take how much time? For one cylinder how much time we will take? We will take 6 multiplied by 30 millisecond. Okay, remember one thing, the question is saying that when you are going from one track to another in the same cylinder, when you are going from one track to another, then it can be done instantaneously. There is no delay. Okay, yes or no? This is already given in the question. You can see that switching between tracks within the same cylinder can be done instantaneously. Okay, so there is no delay there. I hope you understood. So you can see that one track I can read in one rotation. One rotation time is 30 millisecond. So one cylinder has six tracks. So one cylinder time, how much time it will take to read one cylinder? So that will be 6 into 30. So that will be 180 millisecond. Total, how many cylinders you have? Total, we have 2400 cylinders. So remember, for these many cylinders, total how much time it will take? For these many cylinders, it will take this multiplied by this. Okay, yes or no? So you can see that this much time it will take to read all the cylinders. But one more thing you notice. That from one cylinder to next cylinder, when you move when you move to the adjacent cylinder, then that will take 20 millisecond. You can see that seek takes 20 millisecond between adjacent cylinders. Okay, so you can see that when you are going from cylinder 0 to cylinder 1, then it will take 20 millisecond. Okay, when you go from cylinder 1 to cylinder 2, it will take 20 millisecond. Okay, and so on. You can see when you go to cylinder, the last cylinder, what that is 2399. Okay, then like this. So tell me how many moves we are making? You can see total 2399 moves we are making. Yes or no? So you can see that 2399 moves 2399 moves between adjacent cylinders between adjacent cylinders. These many moves between adjacent cylinders we are making. Okay, so that will take how much time? 20 into 2399, these many milliseconds. Yes or no? Is this clear? I hope you understood. That's it. This is your total time. Yes or no? There is no more time will be required. We have considered everything. Okay, so finally your answer will be what? So total time to read entire disk. Total time to read entire disk, what that will be? You can just see this will be 2400 into 180. 2400 into 180, these many millisecond plus you can see 20 into 2399. 20 into 2399 millisecond. Okay, also remember the initial worst case seek, that was 80 millisecond. Okay, so I can say that is 80 millisecond plus. So finally I can say this will be your answer. I hope you understood. Okay, is this clear? Very simple. I hope you understood. One important thing you one imper- one important thing I want to share with you in through this question. Sometimes in the gate exam also it happens that there will be some kind of ambiguity, like should I consider this, should I consider that? Okay, so let me tell you, in this type of questions in the gate exam also you will see that options, they are actually very far away from each other. So sometimes in this type of question, whatever assumption you have to make, okay, if the question has given the complete information, then there is no chance of ambiguity. But if there is some ambiguity, should I consider this, should I consider that, then let me tell you, most of the time it will happen that whatever assumption you make, you will arrive at the correct answer, approximate answer you will arrive, because here you can see that all the options, these are far away from each other. So I don't think that in this question you can make any mistake because of assumptions. Okay, so I don't think, because already these options are very far away from each other. So whatever assumption you make, for example, as I already discussed, okay, about the initial position of the read write head, whatever assumption you make, you can arrive at the correct answer. Okay, so I don't think there is any problem here. But of course, I will edit this question, and in this question I will add one extra line about the initial position of read write head, that I will extra information that I will that I will add. Okay, I hope you understood this. Now let's move on. Let's solve this question from digital logic. Let f be a boolean function and this is f complement, denotes the complement of f. In the options given below, CSOP stands for canonical sum of product. Canonical sum of product, that means this is the min term expansion. And canonical product of sum, CPOS, canonical product of sum, this is your max term expansion. Now, the question is asking which of the following statement is or are correct. The CPOS form, the canonical product of sum form of f, is complement of canonical sum of product form of f. See, this option A can never be true. Do you agree with me? This option A, this is a pure nonsense option. Can you tell me why this is pure nonsense option? Because you can see that a form of f, how can it be complement of another form of f? If you complement any form of f, then you will get f complement, and f complement is never equivalent to f. Yes or no? This is pure nonsense. Actually, I have seen many students, what they write, some teachers also I have seen what they say that canonical SOP is complement of canonical POS. Maybe this type of statement you have also heard. Okay, so let me write it. This type of statement you also may have seen somewhere. This misconception, I've seen some students, they speak like this, that this SOP complement is POS, the complement of SOP is POS. Okay, so these type of statements I've seen some students make, some teachers also make. So these are nonsense statements. Okay, because you can notice SOP, POS, canonical SOP, canonical POS, all these are forms of a Boolean function. If you have a Boolean function, please understand this Boolean function I can write in the SOP form, or I can write in the POS form, or I can write in the canonical SOP form, or I can write in the canonical POS form, or I can write in any other form. Okay, there are many other forms. Okay, yes or no? Or I can write in other form. So you can see that this same Boolean function, I am writing in different forms. These are just different forms of the same Boolean function. Okay, these are different forms of the same Boolean function. So please understand that all these different forms of the same Boolean function, these are basically equivalent. Yes or no? These are basically equivalent to f. I hope you understood. These are equivalent to each other also. These are all equivalent to each other also. Okay, is this clear? Because all of them, they represent f. So this type of statements, these are basically nonsense. Okay, is this clear? I hope you understood. So I hope this point is clear. Okay. Now notice one more thing, that whatever form of f you take, if you complement it, then you will get f complement. F is never equivalent to f complement. Yes or no? F is never equivalent to f complement. Okay. Yes or no? So you can easily see that whatever form of f you take, whether you take canonical SOP, canonical POS, SOP, POS, and if you complement that form, then actually you will get a form of F complement, and F complement is never equivalent to F. Okay, so this point I can say that basically any any form of F, any form of Boolean function F. Now this any form, this can be any form like canonical, this can be canonical SOP, canonical POS, SOP, POS, other. Okay, any form of f if you take, and if you complement it, if this form, if you complement, if you complement, then what you will get? You will get a form of f complement. Okay, yes or no? And very simple point, that this form of f complement, this can never be equivalent to this form of f. Okay, yes or no? So never f is never equivalent to f complement. Okay, so remember, this option A is actually nonsense, pure nonsense option, that canonical SOP form of f is complement of canonical POS form of f. Okay, so this is pure nonsense. I hope you understood this point. So what will be actually the correct statement here? The correct statement will be that instead of complement I should say equivalent. Okay, yes or no? So here actually if I say equivalent, then it will be a correct statement. Okay, so let me write it here, that the correct statements, you can see, if I remove this and if I say that this is equivalent to this is equivalent to this, then I can say this will be a correct statement. Okay, now let's move on to the next statement, option B. Now you can see the question is asking the relationship between canonical form of f complement and canonical form of f. So what are the relationship between them? Okay, this is another very easy. You can notice one thing. Forget about any function, forget about a form of a function. Just a simple point I'm asking you. Let's assume you have two variable, three variable. Okay, let's assume you have variables a comma b. Then on two variables, how many min terms are there? How many max terms are there? Tell me. Let's assume you have variables a comma b. Then if you have two variables a comma b, then how many min terms will be there? How many max terms will be there? Number of min terms on n variable. How many min terms are there on n variable? That is 2 power n. And how many min terms are there on n variable? That is 2 power n. Number of max terms on n variable 2 power n, number of min terms on n variable 2 power n. Yes or no? So if you have variables a comma b, then you can see these are the combinations possible: 0 1 1 0 1 1. Okay, now you can notice that on two variables how many min terms will be there? 4. How many max terms will be there? 4. On n variables how many min terms will be there? 2 power n. How many max terms will be there? 2 power n. So you can see, let me write the min terms here. Means for every combination what will be the min term, and for every combination what will be the max term. Okay, so you can see when you write the min term for any combination, you can see that, let me write it here. If you are having for example x variables, you can see if you are having variables, let's assume x y z w. Okay, now you can see x y z w, and if you take any combination of these, for example let's take 0 1 1 0. Okay, now you can see what will be the corresponding min term and what will be the corresponding max term. Can you tell me the corresponding min term and the corresponding max term? Now you can see that when you are writing min term for any input combination, then when the variable is 0, this we will write x bar. And remember, min term is a product term. Okay, this min term is a product term containing all the variables. So min term is a product term containing all the variables, and max term, this is a sum term containing all the variables. Yes or no? Sum term with all variables. With all variables. And this min term, this is a product term with all variables. Okay, so very simple. Here I can say this min term is a product term containing all the variables. If a variable is 0, we will write it x bar. Variable is 1, we will write it as it is. Variable is 1, we will write as it is, and variable is 0, we will write it w bar. Okay, and you can see in the max term what we will do. This is a sum term. When the variable is 0, we will write it as it is. When the variable is 1, we will write it y bar. When the variable is 1, this we will write it bar, and when the variable is 0, we will write it as it is. Okay, I hope you understood this point. So you can see that if you have a variable v, you can see if the variable v is 0, if the variable v is 1, in this case when variable v is 0, then in min term we will write it v bar, and in max term we will write it v. Okay, is this clear? Very simple. And you can see when the variable is 1, then in min term we will write it v, and in max term we will write it v bar. Okay, and notice min term is basically product term with all the variables, and max term is basically sum term with all the variables. Okay, so here you can easily notice one thing, that for these combinations what will be the min terms. You can see the min term will be a bar b bar, a bar b, A B bar A B. And what will be the max terms? The max terms will be A or B, A or B bar, A bar or B, A bar or B bar. Can you notice one thing? Just some simple observation you make, that every min term is complement of corresponding max term. Yes or no? You can easily see that. This is a very important point, that if you see any min term I, this will be complement of the corresponding max term. Yes or no? Okay, you can easily see what will be the complement of this. What will be the complement of this? So you can see, if I complement AB complement, that will be A bar or B bar. Yes or no? So this is what I'm saying, that every min term is complement of corresponding max term. Let me connect my laptop to charger. So I hope this point is clear, that any min term mi, this is a complement of corresponding max term. Okay, I hope you understood this point. You can see, for example, this is min term 0, this is min term 1, and so on. Okay, you can see 0 1 2 3 4. So any min term I, this is complement of corresponding max term. Okay, the same thing actually you can see here also. Here also the same thing, you can make this observation, that you can see this, if I complement, then this I will get. Okay, yes or no? Complement. So I hope this point is clear. Very simple point. So now let's see the next point. So this is the note number 1. The note number 1, that is that any min term I, this is a complement of corresponding max term. Okay, this is what we have seen. I hope you understood this point. Now let's see the next note. What is the canonical SOP form of a function f? So you can see this is the note number 2. The note number 2 is like this, that what is canonical SOP form of Boolean function f? So this is basically same as your sum of min terms. Okay, this is also called sum of min terms. This is also called sum of min terms. This is also called min term expansion. These are different names for canonical SOP form. Okay, so remember, this is min term expansion of f, or I can say this is sum of min terms of f. I hope you understood. All these things are same, and basically this is basically sum of those min terms where the function value is 1. Okay, in the truth table you find where function value is 1, and the corresponding min term, their summation is your canonical SOP form of f. I hope you understood this point. Okay, very simple. So remember, the another name for canonical SOP form, that is sum of min terms of f or min term expansion of f. And how do we write the canonical SOP form of f? Very simple. In the truth table you find where function value is 1, and corresponding min terms where the function value is 1, the corresponding min terms, their summation, this is your canonical SOP form. Okay, very simple. And what about the canonical POS form? You can see canonical POS form of f. What that will be? The another name for canonical POS form, that is basically product of max terms. Product of max terms of f. Product of max terms. This is also called max term expansion. Max term expansion of f. Okay. And how do we write the canonical POS form? How do we write the product of max term? Very simple. We do the product of those max terms where the function value is 0. Okay, is this clear? Very simple point. I hope you understood. Now notice one thing. If I have, for this function f, if I have canonical SOP form, okay, take this canonical SOP form, assume, or I can say that let canonical SOP form of f, this is equal to, let's assume, for example, because canonical SOP means sum of min terms, yes or no? This simply means sum of min terms. Sum of min terms. Okay, so if you have a canonical SOP form, for example, like this m0 or m3 or M4 like this. Okay, let's assume this is the canonical SOP form. Now you tell me, if I complement it, then what I will get? Let me know. If I complement the canonical SOP form of F, if I complement it, what I'm going to get? Very simple answer. You can see, if I complement it, if I complement, means you are complementing this. Okay, apply the De Morgan law. Apply the De Morgan law. One thing is for sure, that if I complement this, then I will get a form of F complement. Yes or no? I will get a form of F complement. I will get a form of F complement. I will get, yes or no? Because I'm complementing a form of F, so I will get I will get a form of F complement. Yes or no? I told you this point. Any form of F, if I complement, then I will get a form of F complement. Very simple. So let's complement this M0 or M3 or M4. So if I apply the De Morgan law, then what I will get? I will get M0 complement and M3 complement and M4 complement. What is this? You can see that M0 complement, this is a max term 0. This is max term 3. This is max term 4. Yes or no? So did you notice one thing? What is this? This is the product of max terms. Means if I complement the canonical SOP form of F, then I'm getting a form of F complement. But which form of F complement I'm getting? I'm getting product of max terms, and this is called canonical POS form of F. Is this clear? The simple proof, did you understand? Let me know. So you can see, if you have canonical SOP form of F, and if you complement it, then you will get a form of F complement. But which form of F complement you will get? You can see that you will get product of max terms form. So that means this is a canonical POS form of F complement. This is the proof. I hope you understood. Okay, I hope you found this interesting. Very simple. So basically, this is the fact that we are using, that every min term is complement of corresponding max term. Okay, so like this, you can easily get this. Now let's see the next one also. If you have canonical POS form of F, then if I complement it, then what I will get? So you can see that let canonical POS form of F. Let's assume you have this canonical POS form of F M1. Okay, and because canonical POS form, that means product of max term. Yes or no? Product of max terms. Now, for a moment, let's assume that this is the product of max terms. You can see. Okay, let's consider this. If these are the min terms of F, then the remaining will be the max terms of F. Yes or no? These indexes 0, 3, 4. If these indexes, if these are min terms of F, means for these indexes the function value is 1. Then for the remaining indexes, the function value will be 0. Yes or no? So you can see that M1, 2, 5, 6, 7. These will be the max terms. So you can see 1, 2, 5, 6, 7. Okay, yes or no? So you can see, if this is your canonical POS form of F, then if I complement it, this canonical POS form of F, let me complement, then what I will get? I'm complementing a form of F, then definitely I will get a form of F complement. But which form of F complement I will get? You can see, let's complement it. So if I complement it, you can apply the De Morgan law. What you will get? You will get M1, M2, M5, M6, M7 complement, and that will become basically this whole complement. And I can say that if you apply the De Morgan law, it will be like M1 complement plus M2 complement plus M3 complement plus M6 complement, sorry, M2 plus M5 plus M6 complement plus M7 complement, if you apply the De Morgan law. Now finally what you are going to get, you can see that M1 complement, the complement of max term 1, that will be min term 1, then you have min term 2, then you have min term 5, then you have min term 6, and then you have min term 7. The summation of min terms, this is canonical SOP form of F complement. Okay, I hope you understood. So that's it. Very easy. Remember, when I complement canonical purest form of f, I will get canonical SOP form of f complement. When I complement canonical SOP form of f, I will get canonical purest form of f complement. Any form of f, if I complement, then I will get a form of f complement. Okay, is this clear? Very simple. So all these points I hope you understood. Now finally you can see that the canonical SOP form of f complement is complement of canonical SOP form of f. This statement is actually false. Okay, is this clear? Because the canonical SOP form of f complement, that is actually complement of canonical purest form of f. Yes or no? Okay, so this statement is false. What about this statement C? Canonical purest form of f complement is the complement of canonical SOP form of f. Yes, this statement is true. We have seen. And what about the last statement? The canonical purest form of f complement is the canonical SOP form of f. This statement is again nonsense. Why this is nonsense? Because any form of f complement can never be any form of f. Yes or no? So again, this is a pure nonsense option. Pure nonsense option. Because notice one thing, that any form of f complement can never be a form of f, because f and f complement are never equivalent. So how can a form of f complement be a form of f? Yes or no? Any form of f, if I complement, then I will get a form of f complement. If I complement the canonical SOP form of f, then I will get canonical purest form of f complement. If I complement canonical purest form of f, then I will get canonical SOP form of f complement. I hope you understood this point. Notice one more thing in this option B. In this option B, we are saying that canonical SOP form of f complement is the complement of canonical SOP form of f. This is actually false, but notice that this canonical SOP form of f complement, this actually will be equivalent to complement of canonical SOP of f. They will be equivalent, right? Yes, they will be equivalent, because when you complement a form of f, when I am complementing a form of f, then this is basically a form of, this is basically a form of f complement. Yes or no? Which form of f complement? The complement of canonical SOP form of f. This is a form of f complement, but which form? Which form? This is the canonical purest form. Yes or no? Which form? Canonical purest form. And you can see that canonical purest form of f complement, this will be equivalent to canonical SOP form of f complement. Yes or no? Canonical SOP form of f complement. This is equivalent but not equal. Okay, equivalent. This means equivalent but not equal, remember. So this is equivalent to canonical purest form of f complement. Okay, I hope you understood this point. So remember, this is actually equivalent. This means equivalent, not equal. Okay, that's it. So this is the complete analysis of this question. I hope you understood it. In this question, a lot of students have made silly mistake. That is the reason I gave you this question. So I hope all these concepts have become very clear. The min term expansion, max term expansion, the relationship between a form of f and a form of f complement. I hope everything is clear now. Let's move on. Let's solve this question from digital logic based on multiplexer combination circuit. So the question is saying that the minimized expression of the Boolean function ypqr, this Boolean function y, the output of this circuit. So the minimized expression of this Boolean function ypqr implemented by the multiplexer circuit shown in the figure. So this is a very easy question. Here what you can do, first you can find what the output of this left multiplexer. Okay, the output of this left multiplexer, let me write it z. Okay, let me write it z. So first you find what is this z. So tell me what this z will be. You can easily notice here you have 0 1 1 0. This is for exclusive OR. Yes or no? Okay, this is for exclusive OR. So you can see that basically z is basically p XOR q. Z is basically p XOR q. If you did not understand, don't worry. Let's write it here. The truth table, let's write. So you can see that we have S1, S0. Okay, notice one thing, that S0 is your MSB. Okay, because you can see that, for example, in this, here you can see, notice one thing here. Here you can see that, notice one thing here, you have S0, S1, that is basically 0, 1. So notice that S0 is your MSB. Okay, S0 is your MSB. And already this S0 is same as P, and this S1 is same as Q. Okay, so let's see here the truth table. You can see when they are 0, 0, S0, S1, when they are 0, 0, when they are 0, 1, when they are 1, 0, when they are 1, 1. Then you can see what will be Z, the output of the multiplexer. So you can see when both S0, S1, when they are 0, 0, then you can see this 0 will go to the output. Okay, when they are 0, 1, then this 1, this input 1, this will go to the output. So the output will be 1. Now when they are 1, 0, when they are 1, 0, then this input will go to the output. So you can see this will be 1, and finally here 0. Now you can easily see that this Z, this is your exclusive OR. This is the truth table of XOR. Okay, yes or no? So this is the XOR. So finally I can say that Z is basically P XOR Q. Okay, I hope you understood this. Very simple. So once you have this Z which is P XOR Q, once you have this Z, now you can see what will be this Y. Now you have 2 by 1 multiplexer. This R is the select line. Variable R is connected to the select line. So here you can see what you have. You can see when this R is 0, then Y will be Z. Yes or no? So you can see it is like this, that when this R, this select line S. Okay, remember this S is actually connected to this R, is actually variable R is connected to S. Okay, this S is the select line and variable R is connected to that select line. So you can see that when this S is 0, then what will be the output? When S is 0 means R is 0, then the output will be Z. And when S is 1, then the output will be 1. From here, you can write the equation for Y. What will be Y? Y will be basically when R is 0 means R bar. When R is 0, then output is Z. Or when R is 1, then the output is 1. Okay, yes or no? So what we got? We got Y is equal to, R or R bar Z. Okay, now you can apply a property of Boolean algebra. If you remember this property, that A or A bar B, that is basically equal to this A bar you can remove. Okay, so that is same as A or B. Okay, so here the same property you can apply. So what you can say, that R or R bar Z, this R bar you can remove from here. So what you will get? You will get R or Z, and Z is P XOR Q. So finally the answer will be R or P XOR Q. Answer will be option A. So this is a very simple question. Answer option A. In this question also some students have made silly mistake. I don't know why students are making so many silly mistakes. In this type of simple question also, students are making silly mistake. So did you make silly mistake in this question? Let me know. This was an easy question. Traditional question based on multiplexer. Now let's move on. Let's solve this question from digital logic. This is very interesting question, and I think one of the most beautiful question of this test. So let's see this. Consider the Boolean function f a b c d. This function f is given to you. You can see based on variable a b c d, and there is a h also. You can see this h a b c d. The Boolean function h a b c d is unknown. We don't know what is this Boolean function h. The total number of Boolean functions h that will make the function f self-dual. We need to find how many functions h are there such that f will become self-dual. This is what we need to find. Okay, so remember, I'm not asking how many self-dual function f are there. No, I'm asking how many functions h are there such that f will become self-dual. And this question, I have seen that some students, they solved this question with the wrong logic. The logic was wrong, but finally they got the same answer. So it can happen sometimes that with the wrong logic also you can get the correct answer, but it does not mean that the logic is correct. The logic is wrong, but somehow you are getting the correct answer. So in this situation, always learn the correct concept, because in the gate exam they can ask you something else. In the same question, instead of asking the number of boolean functions as, I can ask you something else. Then you will not get the correct answer. So always understand and learn the correct concept. Okay, so let's see what will be the correct concept here. First of all, you can notice I want f to be self dual. First of all, what is the property of self dual? Many students know what is the self dual function. Okay, but let me quickly tell you something which many students don't know. Okay, so you can see this a simple note. Let me tell you from the truth table how you can create dual of a function. Okay, so you can see creating, finding dual of a function from truth table. This is something which many students don't know. Okay, so let me explain this. In goclasses digital logic course I have already explained it. Okay, so you can see with proof, but you can see here I am explaining finding dual of f from truth table. From truth table, if I want to find the dual of f, then how I will find? Okay, so let me just quickly tell you. It is actually very simple. First, you write this truth table in the standard order. Okay, so what you do? Let's assume your function is over three variables. Okay, for a moment, let's assume that your function is over three variables, or it can be over n variables. It doesn't matter. So for a moment, I'm taking this example that our function is over three variable. So first, what you do? You write this truth table in the standard order. Means standard order means 0 to 7. Okay, you can see 0 0 0 0 0 1 0 1 0 0 1 1. Then you can see 1 0 0 1 0 1 1 1 0 and 1 1 1. Okay, is this clear? Let me write the numbering here: 0 1 2 3 4 5 6 7. Okay, now let me tell you, if you have any function f, whatever function f you take on these variables abc, whatever function you take. Okay, let me write here, let me write a0. Okay, means this can be either 0 or 1, of course, yes or no. Let me write a1, let me write a2, let me write a3, a4, a5, a6, a7. Okay, already you know this point that these ai, these are basically 0 or 1. Okay, this point you already know that every ai that is basically either 0 or 1. Okay, 0 or 1, very simple. So you tell me what will be f dual from the truth table. Can you find f dual? This is an interesting question. Means now can you find the f dual truth table? F dual. Okay, means dual of f. So what will be this truth table? What will be this truth table? Can anyone tell me? If you have studied from goclasses digital logic course, then definitely you already know how to find dual of a function from the truth table. So it is very easy. What you will do? First you complement this f and then you reverse it. That's it. Very simple. Okay, so remember, first what you do? You first complement this f. And then what you do? To find f dual, to find f dual, you reverse the f complement. Okay, remember this is the standard truth table. This is the truth table in the standard order from 0 to 7. Okay, so you can see from 0 to 7, from 0 to 7, this is the truth table in the standard order. Now you can see for this f, if I want to find the f dual, then what I will do? First you find this f complement, that will be a0 complement like this. Okay, so you can see it will be a0 bar, a1 bar, a2 bar, a3 bar, a4 bar, a5 bar, a6 bar and a7 bar. Now what you do? You just reverse it. If I reverse it, I will get f dual. This will be f dual. Okay, if I reverse it, then let me tell you what you will get. You will get f dual. Okay, so what will be f dual? Let me quickly write. F dual will be basically A7 bar, A6 bar, A5 bar, A4 bar. Okay, then A3 bar, A2 bar, A1 bar, and A0 bar. Okay. One more observation you can make from this, very easy observation you can make from this, that in F and F dual, what happens? Notice a simple observation you make in F comma F dual. Notice that the F value for combination n, okay, means here this n in the decimal. This is your input combination in decimal. Input combination in decimal. Okay, so you notice one thing, that Fn, this is basically equal to what? You can see from here that, for example, here you can see F0, that is A0. So this will be the complement of this, that will be your F dual for 7. Yes or no? It is like this. It is like this, that Fn, if I complement it, then what I will get? If I complement this Fn, or I can say that this Fn, this will be basically in F dual, this 2 power, okay, for a moment, let me call it M. Okay, so let me call it M. Then you can see in F dual, you find what is 2 power n minus M. This is what you find. Okay, where n is the number of variables. Where n is the number of variables. Then you can easily see that the complement of this, that will be Fm. Okay, so this equation we can create. I hope you understood this. Okay, very simple point. So it is like this. Let me tell you. Basically, from here, what is happening? It is happening that if F is self-dual, let me know if F is self-dual, then what you can say? See, this is a general equation. This is a general equation. Means Fm, that is equal to F dual for 2 power n minus M complement. Okay, means if you complement this, then you will get Fm. Is this clear? For example, if you find what is F, for example, if you find what is F3, then what that will be? That will be in F dual, you find F4, its complement. Okay, it's like this. You can easily see here that what will be F3, means for this combination, what will be F value? That will be basically in F dual, you find F dual 4, and you complement it. Okay, I hope you understood this. A simple observation, nothing else. Okay, so you can see very, very easily, you can see here that F2, what that will be? F2, that will be equal to, in F dual, you find 5. Yes or no? Okay, and you complement this. Is this clear? Very simple. So similarly, you can see that F0, that will be basically in F dual, you find 7 and you complement it. And what will be F1? That will be in F dual, you find 6 and you complement it. Okay. So like this, I hope you understood this point. Now tell me, if F is self dual, then what we can say? Let me know. If F is self dual, if F is self dual, what it means? Self dual, what it means? It means that F is self dual. What it simply means? It means that F and F dual are same. Yes or no? F is self dual if and only if F is equal to F dual. Okay, F is equal to F dual. F and F dual, they are basically same. Yes or no? So now you notice, if F and F dual are same, then what will happen? Then it will happen something like this, that, okay, just let me quickly tell you. Now you can see, this is, for example, if this is 0 0 0 and this is F, now you already know this is 1 1 1. Okay, then just notice, for this 0 0 0, if F is, let's assume, A0, then for this 1 1 1, F is A7, then what will be F dual? You will complement and you will reverse, so it will be A7 complement and it will be A0 complement. Yes or no? So if f and f dual, sorry, if f is self dual, means f and f dual are same, means these must be same. Yes or no? These must be same. So you can see that if f is self dual, then what should happen from here? I can say that a0 should be equal to a7 complement. Okay, means a0 should be different from a7. A0 should be different from a7. Do you agree? If f is self dual, then a0 should be different from a7. Similarly, you notice, what about this, like 001 a1, this is a1, and you can see 110, this is a6. So in the f dual, what will happen? You will complement and you will reverse. So remember this, you will get a6 complement here. Here you will get a6 complement, and here you will get a1 complement. So again you can see that if f is same as f dual, because if f is self dual, means f and f dual, they are basically same, then from here I can say that a1 is equal to a6 complement, and from here I can say that a1 is different from a6. Similarly, you will see that a2 will be different from a5, and similarly you can see that a3 will be different from a4 if f is self dual. Okay, is this clear? If f is self dual, then f and f dual, they will be same, and then this will happen. Okay, what is happening here? Let me write in one line. So you can see that if f is self dual, then what will happen? If f is self dual, then what will happen? Then remember, it will happen that f value for m, that will be different from, f value for 2 power n minus m. Okay, is this clear? Very simple point. So I hope you understood this point. And let me tell you one more thing, that if you see the binary of this, if you see the binary of this, and if you see the binary of this, then you will see that they are basically bitwise complement. Okay, they are basically bitwise complement. If you see the binary of these two, then they are basically bitwise complement. Bitwise complement. I hope you understood this. So this just last point, let me tell you, you can see that if you see the binary of this input combination m, and if you see the binary of input combination 2 power n minus m, then you can see they will be bitwise complement. And what it actually means, let me quickly tell you. You can see if f is self dual, then what will happen? If f is self dual, then what will happen? Let me tell you. You can see a b c, and these are the combinations. Let me just quickly write. Okay, here basically this is the 0, then you can see 001, 010, 011, 100, 101, 110, and 111. Okay, so it will happen like this. You can see 0, 1, 2, 3, 4, 5, 6, 7. Okay, so let me just tell you, as I told you, if f is self dual, this is self dual, so of course f and f dual will be same. Yes or no? F and f dual will be same. So notice this f, how it will look like. It will look like this, that for this combination, whatever value you have here, then that will be different from the value for this combination. And can you notice this combination, they are bitwise complement of each other. Yes or no? These two combination, they are bitwise complement of each other. I hope this is clear. You can see, look at this combination and this combination, they are bitwise complement. This and this, you can see they are bitwise complement. Complement combinations basically. Okay, I can say complement input combinations. These are, I can say that complement input combinations. Complement input combinations. Some authors, they also call them complement input combinations. Some authors also call them mutually exclusive pairs. Okay, this word also, it is used by some authors. So basically they call it mutually exclusive pair. Maybe this word also you have seen sometimes. Okay, so let me just quickly tell you this point, that if you have for A0, A1, and so on, AN. If you consider these two combinations, like for example, if you consider this combination 0, 1, okay, for a moment, let's assume you have A0, A1, A2, A3. Okay, then if you consider, for example, 0, 1, 1, 0, okay, and if you consider 1, 0, 0, 1, then these two combinations, these are basically bitwise complement, and these are, some people call them mutually exclusive pairs. Mutually exclusive pairs. Some people, some authors. Okay, is this clear? So these are basically, some authors, they call them mutually exclusive pair. Now for a self-dual function, what should happen? For a self-dual function, you can see that the function value for these mutually exclusive pairs, or I can say the function value for these bitwise complement pairs, that must be different. Yes or no? So you can see, if if f and f dual are same for a self dual function, f and f dual are same. So for a self dual function, what should happen? You can see that whatever value you have here, you can see if you have some value here, let's assume a0, then remember this value here, it should be a0 complement. Okay, is this clear? Means, for example, here if you have, let's assume function value is 0, then here the function value must be 1. Okay, you can see these two combination, for these two combination, the function value should be either 0, 1 or 1, 0. Here if the function value is 0, then here the function value will be 1. Here the function value is 1, so here the function value will be 0. I hope all these points are clear. So now you can easily see that in a self dual function, what happens? It happens that whatever value you have here, a0, its complement will be here. Okay, very simple. Whatever value you have here, a1, its complement will be here, a1 complement. Okay, whatever value you have here, a2, its complement will be here, a2 complement. And whatever value you have here, a3, its complement will be here, a3 complement. Okay, that's very easy thing. I hope you understood. Okay, so now you can easily solve this question. What was our question? Let's see. So this is our question. Function f is given to us. Let me write it. You can see function f over 4 variables a, b, c, d. And this function f is a bar bc or acd or bd or h. This function h abcd. Okay, this function h is unknown to us. Okay, this is a unknown. This is unknown. Now you can see we want f to be self dual. Okay, we want f to be self dual. Then how many boolean functions h are there? So first what we will do, either you can write the truth table, but the truth table will take 16 rows. So let's make the k map. I think that will be a good way. Okay, so let's quickly make the k map. In the k map, you can see the 4 variable k map I am creating. This is the 4 variable k map. Okay, so you can see here on the column I have AB and on the row I have CD. So you can see this is the area of A, this is the area of B, this is the area of C, and this is the area of D. Okay, now you can see, let me number the cells. So you can see this will be the cell 0, this will be cell 1, cell 2, cell 3. I can say min term. Okay, basically this will be like min term 0, min term 1, min term 3, min term 2, 0, 1, 2, 3. Then you can see 4, 5, 6, 7, then 8, 9, 10, 11, then 12, 13, 14, 15. Okay, is this clear? Very simple point. Now, notice one thing, that 2 power n here, that is basically 2 power 4, that is basically 16. Okay, so Now let's see what this f is bringing. See, f is already bringing some one cells in this k map. Yes or no? There are some one cells in the k map already brought by f. Okay, so you can see without h, without h. Remember one thing, there is or here. So what h can do? H can contribute some one cells, but remember, h can contribute some one cells, but it will never happen that any one cell here will be converted to zero cell. Yes or no? Because there is a or function here. Sorry, there is a or operation here. So remember, if f is already from like without h, let's assume f is 0, then because of h, f can either become 0 or it can become 1. But notice one thing, without h, if f is already 1, then with h also f will remain 1. Okay, this simple point I hope you understood. Very simple. This is or operator here. So without h, for any min term in any cell, if f is already 1, then with h also it will remain 1. But remember, without h in any cell, if f is 0, then with h either it will be 0 or it will be 1. Okay, simple observation this you have to make, because this is or operator here. Okay, now let's see without h, this f where it has one entries, which cells are one cells. So you can see that, for example, a bar bc, this is the area of a bar, this is the a bar area. You can see this is the a bar b area, and this is the a bar bc area. So finally I can say this will be your a bar bc area. So here you have one, here you have one. Okay, now let's see the next acd. This is the a area, this is the ab area, this is the abd area. Okay, so finally I can say this is the sorry, acd. Okay, sorry, acd. So this is the a area, this is the ac area, and this is the acd area. Okay, so remember this is the acd area, so it will be like one here, one here. Next, what about bd? What about bd? You can see this is the b area, and this is the bd area. Yes or no? You can see this is the d area, this is the b area. So the bd area will be this area is the bd area. So one here. Okay, that's it. So far what we got, this is without h. Okay, so I can say this what you got, this is without h. So without h, actually these remaining cells are actually 0 0 0 all. Yes or no? 0 0 0 0 all these cells without h. So please understand that this is your f without h. I hope you understood. Now let's see what should happen. We want f to be self dual. Okay, I want f to be self dual. So if I want f to be self dual, forget about h. What mandatory things should happen? Can anyone tell me? We want f equal to self dual. We want f to be self dual. Then tell me a very simple question I'm asking. If I want f to be self dual, then let me know what are the mandatory things without h, without considering h. What are the mandatory things? If I want f to be self dual, then what should happen? If I want f to be self dual, then remember that fm, this should be different from, this should be different from f16 minus m. Yes or no? Fm should be different from f16 minus m. So for example, if f5 is 1, then f16 minus 5, f11 should be 0. 8 9 10 11 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. A bar bc, a bar bc. Okay, then bd, this is bd, acd, acd 1 1, a bar bc, acd, bd. A bar, BC, ACD, BD. Sorry, actually it will be 15 minus M. It will be 15 minus M. Sorry, so actually earlier also, I think I made a small typo. Sorry, it will be actually 2 power n minus 1 minus M. Okay. So it will be actually 2 power n minus 1 minus M. Okay. So this small typo I did. So you can see that basically from 7 you are removing. So here also it will be 2 power n minus 1 minus M. Okay. You can see. So I think everything else was perfectly fine. Okay. Yes. So we have corrected now. So you can see if f is self-dual, then fm should be different from f15 minus m. Yes or no? Because 2 power n minus 1, that is basically 2 power 4 minus 1, and that is basically 15. Okay, so you can see that if you want f to be self-dual, then what should happen? Fm, where m is decimal value of input combination, so fm should be different from f15 minus m. So for example, f5 is 1, so f15 minus 5 should be 0, means f10 must be 0. Yes or no? It's a mandatory thing that it must be 0. Okay, it's a mandatory thing that it must be 0. F10 must be 0 without H. These are the mandatory things. So far, we did not consider H, but it is mandatory that if you want F to be self dual, then definitely this F10 should be 0. What else? You can see F13 is 1. So F2, 15 minus 13, F2 should be 0. So you can see F2 should be 0. F7 is 1. So F15 minus 7, that is F8 should be 0. You can see. Next, F15 is 1, so F0 should be 0. F6 is 1, so F9 should be 0. F11 is 1, so F4 should be 0. Okay, yes or no? So you can see what we got? Yes. So this is actually without H. This must happen without H. Please understand. Whatever you have here, this must happen without H. Now with H, okay, here I can say that what should I put here, what should I put here, that will be decided by H. Okay, is this clear? I hope you understood this point. So now let's see the next. So you can see that now what H will decide. So you can see because of H, now what should happen? Tell me, what should be the contribution of H? Can anyone tell me the contribution of H? It is necessary that whatever value I have here, means F1, this should be different from F14. Yes or no? So you can see the contribution of H I'm considering. So one thing is very sure that by H, by H, okay, with help of H, with help of H, what must happen? It must happen that F1 should be different from F14. F1 should be different from F14. And this F3 must be different from F12. Yes or no? It is necessary. So tell me what H will do? What H will do? You can see for these two, what choices H has? You just tell me from H point of view, what choices H has for these cells? You can see that What choices H has? Choices for H. You can see that for these two min terms, I can say, or I can say for these two cells, for input combination 1 comma 14, for cells 1 comma 14, for both of them, H has total two choices. Yes or no? What are the two choices? Either 0 1 or 1 0. Do you agree with me? And remember, for the cells 3 comma 12, for these cells also, H has two choices. These are 0 1 or 1 0. Okay, yes or no? I hope you understood this point. Now now remember, what about the remaining cells? What are the choices for H in remaining cells? Because H is also a function on four variables. In the remaining cells, what are the choices for H? Because remember, H is also a function on four variables A, B, C, D. So tell me, just let me know, choices for H in the remaining cells, what that will be. You can notice where F is already 0 without H, where F is mandatorily 0, there H cannot be 1. Do you agree with me? Yes or no? Okay, very simple point. I am saying note that, you note that cells, F cells like without H, there are some cells where F must be 0. Do you agree with me? Yes or no? Without H, without H, those cells, without H, remember, those cells where F is, F must be 0. F must be 0. What were these cells? What were the numbers of these cells? Let me tell you. You can see these cells, for example, 0 4, 0 to 4. You can see cells 0 to 4, and you can see 8 9 10. Okay, yes or no? 8 9 10. So please understand that without H, those cells where F must be 0, so their F cannot contribute 1. Yes or no? Their H, there, because of H we cannot have 1, so their H cannot have 1. Okay, yes or no? Because already there is over here, there is over here. So you can easily see that in these cells H has only one choice. Yes or no? So for these cells H has one choice. So for these cells H has one choice, that is 0. Yes or no? H must be 0. Okay, so for these cells H must be 0. Okay, but what about the remaining? Let me know. You can see without H, those cells where F is already 1, okay, where F is already 1, their H can be 0 or 1. Yes or no? Their H can have value 0 or 1. So you can see that without H, those cells where F is already 1, already 1. Which cells were these? What were the cells number? You can see the cells number were basically, you can see 5, 5, 6, 7. The cells number were 5 6 7. You can see 5 6 7, and then 11 13 15. Okay, 11 13 15. Okay, so you can see that where F is already 1, without H, where F is already 1, there H has two choices. Okay, yes or no? For these cells H can be 0 or 1. H can be 0 or 1. So finally you tell me what will be the answer? What will be the number of H? You can see. So number of functions H. So number of functions H which make number of functions h which make f self dual. So that is very simple. The answer will be 2 multiplied by 2. This 2, this is for cells 1 comma 14. Yes or no? For cells 1 comma 14, two choices. Then for cells 3 comma 3 comma 12, again two choices multiplied by, you can see 2 power 6. Okay, this is cells where f is already 1 without h. Yes or no? Cells where f is 1 without h. Okay, so that's it. So finally your answer will be 2 power 8, that is 256. Okay, so that's it. I hope you understood this. So this is the complete analysis of this question. So I hope this has become very clear to you how to solve this question. What is the correct logic to solve this question we have seen. Okay, just at the end, let me write the note basically about the self dual. Okay, so you can see that if f is self dual, if f is self dual, then what should happen? Then remember, fm should be different from f 2 power n minus 1 minus m. Okay, where n is the number of variables. Okay, where n is the number of variables like a0, a1, and so on, an. So where n is the number of variables, and this m, this is basically decimal decimal value of input combination. Value of input combination. Okay, I hope this point is clear. And one more thing, that if you look at this, one more note, if you look at this m comma 2 power n minus 1 minus m, if you see their binaries are bitwise complement. Okay, so you can see their binary are bitwise complement. Okay, so very simple. I hope you understood this point. Everything is clear, let me know. Let's solve this question from digital logic multiplexer based question. The question is saying you have to make a 2 power n by 1 multiplexer, a multiplexer with 2 power n inputs, 1 output, using only 2 by 1 multiplexers. The number of 2 by 1 multiplexers needed, what that will be? Means to make 2 power n by 1 multiplexer, what is the number of 2 by 1 multiplexer will be needed? And remember, we have to use only 2 by 1 multiplexers to create 2 power n by 1 multiplexer. Okay, so this is actually a very simple question. You can take one example, like you can create 8 by 1 multiplexer using 2 by 1 multiplexer. Okay, so let's do one thing. So you can see, let's build 8 by 1 mux using 2 by 1 mux. Okay, so this is actually very easy. You can see overall what I want 8 by 1 multiplexer. This is overall I want. Inside I will use 2 by 1 mux, but overall from the outside it will look like a 8 by 1 mux. Yes, correct. Okay, from the outside it will look like that there are 8 inputs, and there is only one output. Yes or no? From the outside it will look like this, but inside we are using 2 by 1 muxes. 2 by 1 mux has 2 input, 1 output. So it is very simple, that what you do here, you need to put a 2 by 1 mux. This 2 by 1 mux, it will take care of these two inputs. This 2 by 1 mux, it will take care of these two inputs. this 2 by 1 mux, it will take care of these two inputs, and this 2 by 1 mux, this will take care of these two inputs. Now these 2 by 1 muxes, they also have 1 output. So now you have total 4 lines. So you can see 2 by 1 mux, it can handle two inputs, yes or no. So another 2 by 1 mux you will put here. Okay, on the next level you will put another 2 by 1 mux, it will take care of these two inputs, and another 2 by 1 mux you will put here, it will take care of these two inputs. Okay, yes or no. Now again you have two outputs. So we want one output, please understand. Overall, from the outside, it will look like 8 inputs, one output. Overall, I want one output. But here I am getting two output. So another 2 by 1 multiplexer I can put. Okay. Another 2 by 1 multiplexer we can put. This 2 by 1 multiplexer, it will take care of these two, and it will give you the output. Okay. So like this. I hope you understood. Very simple, right? So you can notice, if I want to create 8 by 1 mux, then on the first level, let's call it first level, let's call it level 1. On the first level, how many 2 by 1 mux we need? That will be half, yes or no, because one multiplexer, one 2 by 1 multiplexer can take care of two input lines, yes or no. Is this clear? So on the first level we need half. I can say, if you have, for example, 8 inputs, then half means 4 2 by 1 multiplexer I need at the first level, then 2 2 by 1 mux at the second level, then 1 2 by 1 mux at the third level, like that. Okay, yes or no. I hope you understood this. So overall, if you want to build 2 power n by 1 mux using 2 by 1 mux, then tell me, on the first level, how many 2 by 1 mux you need? Let me know. You can see, total we have 2 power n inputs. From outside, it will look like 2 power n by 1 mux. Okay, so remember, it is like this. It is like this. So you can see, on the first level, how many 2 by 1 mux we need? You can see, one 2 by 1 mux, it can take care of two input lines. So for two input lines, one 2 by 1 mux you need. For these two input lines, another 2 by 1 mux you need. Okay, yes or no? And so on. For these two inputs also, another 2 by 1 mux you need. And for these two inputs also, another 2 by 1 mux you need. So on the first level, how many 2 by 1 muxes you need? That will be half the number of inputs. Yes or no? So you can see, on this first level, total we need 2 power n minus 1. These many 2 by 1 muxes. Okay, yes or no? Then you can see, now what we have. Now here we have how many these output lines? So that is 2 power n minus 1 output lines we have here. Okay, these are basically 2 power n minus 1 output lines of the first level. Lines from first level. From first level. Okay, so what we need? Okay, the same thing recursively you can do. So now these two lines we can handle with 1 2 by 1 mux. Okay, so like that. So you can see, on the second level, how many 2 by 1 muxes will be needed? This 2 by 1 mux you can make, then this 2 by 1 mux, okay, and so on and so on. So tell me, how many 2 by 1 muxes on the second level? So that will be half the number of input lines here. Okay, from the second level point of view, these are the input lines, yes or no? From the second level point of view, now these are the input lines, so half of them. Okay, so here I can say that we need 2 power n minus 2, these many 2 by 1 muxes. Okay, and remember, this same thing we will continue till when? The same thing we will continue till at the end there is only 1 2 by 1 mux you need. Okay, so and so on, basically here only 1 2 by 1 mux you need. Okay, so like this. So it is a GP actually. What you are getting, let me tell you, you are getting a GP. So you can see that number of 2 by 1 muxes, or I can say that number of 2 by 1 muxes needed. Number of 2 by 1 muxes needed, what that will be? That will be equal to, that will be a GP series. You can see on the first level 2 power n minus 1 these many, then on the second level 2 power n minus 2 these many, then 2 power n minus 3 these many on the next level, keep going like this till the 1. This 1 simply means 2 power 0. Okay, yes or no? So this is a GP. It is a GP series, GP summation. Yes or no? So basically GP summation. Okay, so the GP summation, what that will be? That will be A. Okay, consider this as the first term. So you can see A into R, that is 2, common ratio, that is basically 2. A into R power number of terms, the number of terms from 0 to n minus 1, the number of terms, that is basically n minus 1 divided by R minus 1. So you can see it will be 2 power n minus 1. These many 2 by 1 muxes needed. Okay, I hope this point is clear. Very simple question. So this is a very simple question. For this question the answer will be 2 power n minus 1. Yes or no? 2 power n minus 1. These many 2 by 1 muxes will be needed. So this is a very simple question. I hope you understood. Okay, now let's move on. Now let's solve this question. Actually, for this question, I have already provided the detailed video solution with complete analysis. I have already provided, so you can check it out. You can see this is a question based on SR latch with NAND gates. Okay, this is a SR latch with NAND gates. So you can see this is the complete question. This is, you can see this is the complete question. Now let me tell you, I have already provided the detailed video solution on the Gate Overflow website under this question. Okay, you can check it out under this question on the Gate Overflow website. The detailed explanation, you can see, with detailed video solution is provided. So just go through this detailed video solution. Also, let me tell you, there are many variations also I provided. All these questions I have solved in this single session. Okay, basically all these questions, you can see gate CS 2004, gate IT 2007, gate ECE 2017, gate ECE 2007, gate EC 2009, gate EC 2023. All these questions I have solved in this single session. So what you can do, let me tell you, on YouTube you can search on YouTube, just search on YouTube goclasses SR latch. Okay, on YouTube you can search goclasses SR latch. Okay, so you will find this video. This is just a 2 to 3 hour video, let me tell you. But in this video we have the complete summary and all these gate PYQs. Okay, is this clear? So you can see that the complete summary of SR latch, the complete summary with all the gate CS and gate EC previous year questions in this single video you can find. Okay, so on YouTube today you can search goclasses SR latch, you can search and you can watch it. The link I will provide you in the description, in the pinned comment also. Okay, below this video, in the description, in the pinned comment, you can find this link also, or you can search on YouTube, or you can find on the Gate Overflow website under this question. This is the complete question on the Gate Overflow website under this question. This explanation is already provided by me. Okay, you can watch it. Now let's move on. Let's solve this question from discrete mathematics, mathematical logic, propositional logic. The question is saying there are two villages X and Y. It is known that each person from village X always tells the truth and each person from village Y always lies. You meet three people ABC who are from these villages. You are told that AB are from the same village. This information we already have, that AB are from same village. A says, if B is from village X, then I am from village Y. C says, if I am from village X, then 2 plus 2 equal to 4. What can you infer about the villages to which ABC belong to? Very simple question. There is a village X and there is a village Y. You can see the question is saying that village X people, you can see it is already known that village X people always tell the truth. Okay, so remember these village X people, these are the truth speaking people. Truth speaking people. Okay, and you can see these village Y people, these are the liars. Okay, they always lie. It is given that the village Y people, they always lie, and village X people, they always tell the truth. Okay, so now the question is saying that ABC people you meet, and remember it is already given that AB are from same village. Okay, so remember AB, these are from same village. These are from same village. Okay, means either they are from village X or they are from village Y, both. Yes or no? Okay, now let's see what statements they are making. You can see this A says, okay, remember now the statement by A. What A says? A says that, let me write what A is saying in the propositional logic expression. So you can see A is saying that if B is from village X, means XB. Yes or no? If B is from village X, then, okay, this is if then statement. If B is from village X, then I am from village Y. Okay, if B is from village X, then I am from village Y, means A is from village Y. This is what A is saying. Okay, and you can see what C is saying. C is saying that if I am from village X, then 2 plus 2 equal to 4. Okay, if I am from village X, means XC, means C is from village X, then 2 plus 2 equal to 4. Okay, if I am from village X, means you can see C is from village X, then 2 plus 2 equal to 4. Okay, one thing you notice here, immediately you notice here, this 2 plus 2 equal to 4, this is actually true. Yes or no? Anything implies true. What is that? Tell me. In propositional logic, anything implies true. What is that? Anything implies true. That is true. Yes or no? So this is true. So you can see that what C is saying, that is truth. C is speaking truth. So can C be from village Y? This C, can it be from village Y? No, it cannot be from village Y, because remember village Y people, these are liars always. Okay, and village X people, these are truth speaking people always. So notice one thing, that C is speaking the true statement. Overall, this statement is true. Why? Because anything implies true. That is true. So C is speaking a true statement. Then definitely C cannot be from Y. And already the question is saying that ABC, these people are from either X or Y. Yes or no? These people ABC, these are from these villages. You can see you meet three people who are from these villages. So definitely C is from village X. Yes or no? From here I can say that C, this we can conclude. We can conclude that C is from village X. Yes or no? From village X, because C is speaking the truth. So C is definitely from village X. Okay, what about A comma B? Already it is given that A comma B, these are from the same village. Okay, so I can make two cases. Notice, now I will make two cases here. Okay, so you can see here what I will do. Notice here I will make two cases. What are the two cases? The two cases are that they are from X, that they are from Y. Okay, so let's understand these two cases. Okay, notice A comma B, these are from same village. So the case number one that they are from village X. A is from village X, B is from village X. And what is case 2? That is they are from village Y. A comma B both are from village Y. Okay. Already what statement A is saying, you can see A says that if X is from if B is from X, then I am from Y. Okay. This is what A is saying. A is saying that if B is from X, then I am from Y. Okay. Now you notice if they are from village X, then this statement should be true statement. Do you agree with me? In this case number 1, if they are from village X, you can see I'm assuming that they are from village X. If they are from village X, then this statement should be a true statement. Yes or no? If this statement should be a true statement, already what we know? We know that this X A comma XB means A comma B, these are from X. So already what we know? We know that A is from Y. This is false. Okay, because already in this case number 1, we are assuming that A comma B, these are from village X. So I can say that this XB, this is actually true. Okay, and you can see this YA, this is actually false. True implies false. That is false. So there is a contradiction. Do you agree with me? Overall, did you notice that there is a contradiction? Because true implies false, that is false. But I am assuming that A is from village X. So A is speaking the truth, but actually this statement is actually false. So again, did you notice that in this case number 1, we got a contradiction? We got a contradiction. So definitely case number 1 is not possible. Okay, is this clear? Let me know. So you can see this implication is false. So definitely you can see that here there is a contradiction. Okay, yes or no? Contradiction. Very simple. Okay, now let's see the next. Definitely case number 1 is not possible. So let's see the case number 2. In the case number 2, you notice I am assuming that both are from village Y. If they are from the village Y, then this thing will become true. Yes or no? If they are from the village Y, then this will become true. Overall, this statement will become true. Overall, this statement will become true. But notice, if they are from village Y, then actually A must be a liar. If they are from village Y, then A must be a liar. Means actually this statement must be false. But it is becoming true. So again, there is a contradiction. Remember, if they are from the village Y, then A must be speaking the false statement. This is what A is speaking. It must be a false statement. But you can see this is actually becoming true because anything implies true, that is true. Because in this case, YA is true. Okay, so you can see that what A is speaking, that is actually true, but it should be false. So again, there is a contradiction. So in this case too, also what we got? We got contradiction. So basically, I think this question has some error because I can say that it's not like we cannot derive, it's like this information is contradictory. So for this question, what will be the answer? For this question, the answer will be, let me tell you, you can see we cannot infer this, we cannot infer this. All of them are from village Y, from village X. We cannot infer this. The given information is insufficient to infer the villages they belong to. Actually, even this is also not correct. Okay, honestly speaking, this question has a mistake. This question is taken from a standard top university. I think this question is taken from some very nice exam. Okay, I forgot the source, but as it is, this question is taken from some very nice exam. I think this mistake was there in that exam itself. Okay, basically this question from the standard resource from where this question I have taken, I think this mistake is there in this question. Here, basically, I can say the correct answer will be that this complete information is, this is a contradictory information. This is basically contradictory information. Okay. So I think that you can tick option D. If you ticked option D, we will consider this as the correct answer. Okay. So let me tell you that I think you have ticked D, right? Yes or no? So those who marked D, this we will consider as correct. Okay, we will consider correct. Actually, it is not correct, but we will consider correct. Okay. Actually, option D is also not correct because option D is saying that the given information is insufficient to infer the villages to which ABC belong. Notice one thing. If I give you some extra information, then also already we got a contradiction. So it's not like contradiction will be gone. With additional information, can the contradiction be gone? If I give you, let's assume, some additional information. Okay, I give you one statement more, maybe two statement more, take more information from me. Then can I say that you can still it is contradictory? Do you agree with me what I'm saying? Option D is actually not correct because option D is saying that the given information is insufficient to derive the knowledge about the villages of ABC. But actually, I am saying that this information already it is contradictory. So if I give you some more information, some more statements, if I give you, then also the contradiction will not go away. Do you agree with me? If I want contradiction to go away, then what I need to do? Some statement I have to change in this question. Some statement I have to replace, some statement I have to change. Then the contradiction will go away. So actually for this question, none of the option is correct at this. If this question is as it is, then none of the option is correct. But I think that during the mock test, during the test, if you marked D, then we will consider that as correct. Okay, I will change the answer key. And I hope this has become clear. Anyway, the analysis of this question, has it become clear? Don't worry about this question. Just tell me this point, that the analysis of this question, is it clear? So I hope you understood. So this type of questions, similarly, you can handle. Okay, let's move on now. Let's solve this question from discrete mathematics graph theory. This is a very simple and beautiful question. This basically is asking you the definition of isomorphism. You can see two graphs are given to you, G, H, and they are isomorphic. This information is already given to you. You don't have to check whether they are isomorphic or not. They are already given that they are isomorphic. Now the question is asking, indicate the alternative that justifies this statement. Means find the statement which will prove that they are isomorphic. Okay, yes or no? Basically we have to find a statement which can prove that they are isomorphic. Okay, basically statement that proves, statement that implies G, H are isomorphic. G, H are isomorphic. Okay, is this clear? So we want that statement which will imply that G, H are isomorphic. That statement we have to find. Okay, now notice the statement A is saying the degree sequence is same. Does it imply that two graphs will be isomorphic? Tell me. If degree sequence of two graph is same, does it imply that those graphs are isomorphic? No, this statement does not imply that graphs are isomorphic. But remember, if degree sequence is different, then definitely it will imply that graphs are not isomorphic. So actually, we can use this degree sequence to prove non-isomorphism, but we cannot use it to prove isomorphism. Okay, is this point clear? Very simple point. Remember, here I can say that if you have same degree, okay, let's assume you have two graphs G comma H, and these G comma H, they have same degree sequence. Same degree sequence. Then remember, same degree sequence does not prove, this does not imply that G comma H are isomorphic. Okay, yes or no? G comma H are isomorphic. But remember, if you have different degree sequence, if degree sequence is different, then that definitely proves that graphs are not isomorphic. If you have different degree sequence, from here you can definitely say that graphs are not isomorphic. Okay, I hope this point is clear. So remember, having same degree sequence does not imply that the graphs are isomorphic. Okay, very simple point. You can easily create two graphs which are not isomorphic, but their degree sequence actually will be same. Okay, this type of graphs you can easily create. Okay, you can try it, you can do it. So I hope this is clear. For example, let me create. Okay, you can consider. Let me consider this graph. Let's consider a cycle on 6 vertices. Okay, you can see. Consider this C6 cycle on 6 vertices. You can see degree 2, 2, 2, 2, 2, 2. Yes or no? Now you can consider another graph which is disconnected, but here also you can see the degree sequence will be 2, 2, 2, 2, 2. Yes or no? So you can see that having same degree sequence does not imply that graphs are isomorphic. Okay, yes or no? Is this clear? So I hope you understood this point. So you can see, let's call it, for example, this C6, let's call it G, let's call it H. But definitely you can see that G is not isomorphic to H. Okay, is this point clear? So remember, this statement does not justify that these graphs are isomorphic. This statement does not imply that these graphs are isomorphic. Okay, let's see the option B. Option B is saying the graphs have same number of vertices and same number of edges. This also does not prove, this also does not imply that these graphs are isomorphic. Okay, so again you notice you have graph G comma H. If you have same number of vertices, and edges, same number of vertices and same number of edges, then remember, this does not imply that graphs are isomorphic. Very easily you can create counter examples where where graphs are not isomorphic, but they have same number of vertices, same number of edges. Okay, so you can see that this also does not imply isomorphic. But you can see if you have different number of vertices, if you have different number of vertices, if you have different number of vertices, then remember, this will definitely imply that graphs are not isomorphic. Similarly, if you have different number of edges, then that will also imply that graphs are not isomorphic. Okay, I hope you understood this point. So you can easily create a counter example. Tell me what counter example you will create with same number of vertices, same number of edges. Okay, so yes, I think this previous will work, right? Yes or no? You can take this as G. Here you have total 6 vertices and 6 edges. Yes or no? And you can consider this C6. Okay, you can consider here you have again 6 vertices, 6 edges. Okay, so you can see here this is G, this is H. Notice they have same number of vertices, same number of edges, even same degree sequence, but still they are not isomorphic. This G and H, they are not isomorphic. Okay, yes or no? So I hope you understood this point. Very simple. So basically, this statement does not imply that they are isomorphic. This statement does not justify that they are isomorphic. Also, next, what about option D? Each vertex of G and H belongs to exactly four distinct triangles. Each vertex of G and H belong to exactly four distinct triangles. Let me tell you, actually, whatever property you take, there is no single property which can prove that they are isomorphic, which can imply that they are isomorphic. Only the definition can imply that they are isomorphic. Okay, actually, this option D, you can find counterexample for option D also. Actually, you can consider maybe 10 properties. You can consider, let me tell you, you can consider same number of vertices, same number of edges, same degree sequence, same chromatic number, same number of three length cycles, same number of four length cycles, same number of five length cycles, same diameter. Basically, you can consider 20 properties. You can consider, then also I can create a counter example where all those properties, all those 20 properties will satisfy, but still the graph will be non isomorphic. Are you getting my point? Very simple point. Remember, these properties like number of vertices, number of edges, number of three length cycles, number of four length cycles, connectedness, the diameter, the chromatic number, the degree sequence. Okay, all these properties we can use to eliminate the options. But remember, if you have, let's assume 20 properties are satisfied by graph G comma H, but still remember they can be non-isomorphic. Okay, I hope you understood this point. So basically, if you want to prove that graphs are isomorphic, if you want to justify that graphs are isomorphic, then there is only one way. There is only one way, that is the definition of isomorphism. And what is the definition of isomorphism? Two graphs are isomorphic if and only if there exists a bijection between their vertices. Between their vertices, there exists a bijection which preserves the adjacency. Okay, so remember this option C, this is the definition of isomorphism. Only this can prove that the graphs are isomorphic. Only this can justify that the graphs are isomorphic. Only this can imply that the graphs are isomorphic. So the answer will be option C. This option C, this is the definition of isomorphism. This is the definition of graph isomorphism. Okay, so let me tell you this point, that graph isomorphism definition, you can see G comma H are isomorphic, if and only if, okay, if and only if G comma H are isomorphic, if and only if there exists a bijection between vertices of G comma H which preserves adjacency. Okay, so basically I can say that there exists a bijection, there exists a bijection, there exists a bijection from vertex from VG to VH, okay, such that it preserves adjacency. What that means? Such that it preserves adjacency. Now what that actually means? It preserves adjacency. Now what this actually means, adjacency. So let me tell you what this means, like this statement, preserving adjacency. What this means? Let me tell you. It means that see, let's call this bijection F. Okay, there exists a bijection F. There exists a bijection F. Bijection F. Such that, okay, there exists a bijection F from VG to VH. Okay, so now let me tell you that this bijection from VG to VH, this bijection must preserve adjacency also. It must be a bijection from VG to VH first of all. This is the one thing, that it must be a bijection. There exists a bijection from VG to VH so that it preserves adjacency. Now preserving adjacency, what it means? It means that A comma B are adjacent if and only if, it means that A comma B are adjacent, P are adjacent. Two vertices. I am talking about two vertices. A comma B are adjacent if and only if and only if F A comma F B are adjacent, are adjacent in H. Okay, see, very simple point. I am saying that A comma B are adjacent in G, A comma B are adjacent in G, if and only if their images Fa comma Fb they are adjacent in H. Okay, is this clear? And this would happen for all A comma B in Vg. Okay, so remember, this would happen, this would happen, this would happen for, this would happen for all A comma B in Vg. This would happen for all A comma B in Vg. Okay, I hope you understood this point. Is this clear? Let me know. Very simple. This is the definition of isomorphism. G comma H are isomorphic if and only if there exists a bijection. Okay, some bijection exists. At least one bijection exists. There exists a bijection between the vertices of G comma H. Okay, there exists a bijection between vertices of G comma H such that it preserves the adjacency. Preserving adjacency means for all the pair of vertices, I can say that they are adjacent in G if and only if they are adjacent in H. Means if two vertices are adjacent in G, then their images should be adjacent in H. If two vertices are not adjacent in G, then their images should not be adjacent in H. Okay, very simple. So this is the definition. I hope you understood. Okay, so just using this definition, we can prove that graphs are isomorphic. Other than this definition, there is no property which can prove that graphs are isomorphic. Even 20 properties combined cannot prove that graphs are isomorphic. Only this definition can prove the graphs are isomorphic. Only this definition can justify that two graphs are isomorphic. Using properties, we can eliminate the options. I can say all these properties like same number of vertices, same number of edges, same degree sequence, same chromatic number, same number of 3 length cycles, same number of 4 length cycles, same diameter, connectedness. All these properties that we use to eliminate the options, all these properties, these are basically the necessary conditions for isomorphic graphs. These are not sufficient conditions for isomorphic graphs. Okay, is this clear? All these properties, these are for isomorphic graphs. If two graphs are isomorphic, then these are the necessary conditions, but they are not sufficient. Like using these properties, you cannot prove that graph are isomorphic. But if the graph is already isomorphic, you know that G comma H are isomorphic, then all these properties will satisfy. So all these properties, these are necessary properties for isomorphic graphs. Okay, these are necessary properties for graphs to be isomorphic, but these are not sufficient to prove that graph is isomorphic. Okay, is this clear? I hope you understood. So this is a beautiful question. This is basically on the definition of isomorphism. Do you really understand the property? I can say the concept of isomorphism, the definition of isomorphism. I hope you understood this. Now let's move on. Let's solve this question from discrete mathematics group theory. Let S be a set 0, 1, 2, 3, 4. This is a subset of Z. Z means integers. So yes, this is a subset of integers equipped with binary operations hash and at the rate. Okay, hash comma at. So basically these two operations we are defining on this set S. Now these operations are defined by the tables given below. Two tables are given, one for operation hash, one for operation at. You can see, based on these operations, consider the following statements. Now this is the complete question. These statements are given to you. Of course, we need to find which of these statements are true, which of these statements are false. So let's solve it. Let's see the first statement. The first statement is saying that the operation at satisfies the commutative property. For commutative property, what you will check? See, these tables are given to you. These are called Kelly table. You can call them Kelly table. You can call them multiplication table. You can call them operation table. These are different names for this table. So I can call them operation table. I can call them multiplication table. I can call them Kelly table. Now let's call them operation table. Now you can see that from the operation table, if a operation table is given to you, then how to find whether the operation is commutative or not? So what you will do, you will just check that the transpose of this matrix, see this is a matrix, right? Yes or no? Okay, so this is basically a matrix M. This is like matrix M. Okay, so what you will do, this is your matrix M. Now what you will do, I can say that this operation table M is commutative, this operation is commutative, I can say this at is commutative, at is commutative, or I can say has. Okay, let's, has is commutative if and only if and only if this M is same as M transpose. Okay, this M is same as M transpose. So very simple, that M is same as M transpose. Okay, this means M transpose. What it means? It actually means that the row for 0, this should be same as column for 0. Row for 1 should be same as column for 1. Row for 2 should be same as column for 2. Row for 3 should be same as column for 3. Row for 4 should be same as column for 4. Okay, check it. You can see row for 0, is that same as, this is the row corresponding to 0. Is it same as column corresponding to 0? Yes. This is the row corresponding to 1. Is it same as column corresponding to 1? 1 2 3 4 0, 1 2 3 4 0. Yes. This is the row corresponding to 2. Is it same as column corresponding to 2? 2 3 4 0 1, 2 3 4 0 1. Yes. This is the row corresponding to 3. This is the column corresponding to 3. Are they same? 3 4 0 1 2, 3 4 0 1 2. Yes. This is the row corresponding to 4. This is the column corresponding to 4. Are they same? Yes, they are also same. So yes, this has is definitely commutative. Okay, the operation is commutative. Yes, this statement is true. Now what about the next? What about the next, like this at, what about this? Again the same thing you check, means the row for 0, the row corresponding to 0, is it same as column corresponding to 0? Yes. The row corresponding to 1, is it same as column corresponding to 1? 0 1 2 3 4, 0 1 2 3 4. Yes. Row corresponding to 2, is it same as column corresponding to 2? 0 2 4 1 3, 0 2 4 1 3. Yes. Row corresponding to 3, column corresponding to 3, are they same? 0 3 1 4 2, 0 3 1 4 2. Row corresponding to 4, column corresponding to 4, are they same? 0 4 3 2 1, 0 4 3 2 1. Yes. So remember, this at satisfies commutative property. This statement is also true. Okay. Now let's see the next. That is, in the operation hash, 0 is the identity element. Now what about the identity element? When can I say an element is identity element? So remember, in the operation table, in in the operation table, in the operation table, remember, in the operation table, an element E is identity element. An element, identity element is also called neutral element. Remember, there is another name for identity element, that is neutral element. Okay, so basically E is called identity element if and only if, when can I say that E is identity element? E will be called identity element, E will be called identity element if the row corresponding to E, the row corresponding to E, that should be same as this horizontal header, and the column corresponding to E, that should be same as this vertical header. Okay, so you can see that the row corresponding to E, that should be same as horizontal header, horizontal header. Okay, and you can see the column corresponding to E, and the column corresponding to E, that will be same as vertical header. Okay, I hope this point is clear. Very simple, right? Okay, so remember here, look at this operation table for operation hash. Here you can see that this 0 is the identity element, because you can see this row corresponding to 0, that is same as this horizontal header, and this column corresponding to 0, that is same as this vertical header. Okay, yes or no? Next you can see, what about this at you can see here, notice one thing, that this 0 is definitely not identity element for at. For at I can say 0 is not identity element, but maybe something else is identity element, that also we have to check, yes or no? See, 0 is not identity element, that is fine, but what about the other elements? You can see that this row corresponding to 1, that is same as the horizontal header, and this column corresponding to 1, this is same as this vertical header, yes or no? So remember, for this for this at I can say that 1 is the identity element. Is this clear? This 1 is the identity element. I hope you understood. So remember, this statement in the operation hash 0 is identity element, this is true. In the operation at, there is no identity element, this is false. Actually 1 is the identity element for at. Okay, is this clear? So for this question, remember, 1, 2, 3, these are the true statement. The fourth, this is the false statement. I hope you understood this question. Okay, so very simple question from the group theory. The group theory complete summary is available on the Go Classes YouTube channel. Okay, on YouTube you can search Go Classes group theory. Go Classes group theory on YouTube. Okay, just search it. On YouTube you search it. Then you will find that there are 3 lectures, and in these 3 lectures the complete group theory I have covered. Just 3 lectures, that's it. 3 lectures and the complete group theory I have covered. Okay, now let's move on. Now let's solve this question from relations in discrete mathematics. Let R be a relation on set A. Set A is the base set ABCD. R is a relation on this set A defined by reading the columns of the following table from top to bottom. If a column in the table reads XY1, it means X is related to Y in R. If a column in the table reads XY0, it means X is not related to Y. Okay, for example, here you can see AA0 means A is not related to A. BA0 means B is not related to A. CA1 means C is related to A. Okay, this is what the question is saying. Notice one thing. You can see, for instance, from the fifth column, you can see this fifth column here, AB1. It means that A comma B. It means that this ordered pair AB, this belongs to R, means A is related to B in R. Okay, you can see from the second column, you can see that B is not related to A in R. Okay, you can see BA0 means B is not related to A in R. Okay, now the question is saying that another relation S on the same set A is defined as following. For any xy belonging to A, whatever 2 elements you take from A, same or different. Okay, for all xy belonging to A, the pair xy is in S if and only if there exists a z in A such that both xz and zy belong to R. Then what is the cardinality of S? This is actually a very simple question. You just understand. First, you understand the relation R. You can see in this relation R, this is a relation on set A. Okay, and this relation has ordered pairs. So you can see that A is not related to A. Okay, because here you can see, just find where is 1. This is 1, means C is related to A. Okay, so C is related to A. Next you can see A is related to B. Next you can see A is related to C. Next, B is related to C. Next, D related to C. Okay. Next, you can see C related to D, like this. So, what are the size of R? Size of R, that is 1, 2, 3, total 6. Yes or no? You can say size of R, you can count from here. Like, just count how many ones are here. So, you can see total how many ones we have here? 4, 6. Okay, yes. So, very simple. This is the size of R. Now, remember, we are defining a relation S on A. On the same base set, we are defining another relation. And we are saying that X will be related to Y if and only if there is some Z such that X is related to Z, then Z is related to Y. Okay, basically, X is related to Y in S if X is related to Y in R transitively. Yes or no? Okay, are you getting my point? See, very simple. What I will do, first you make the graph representation of R. Let me tell you, in this type of question, the graph representation is the best representation. So just make the graph representation of R. Okay, let's make this graph representation. You can see the elements in the graph representation of any relation. The vertices will be the elements of the base set. So A, B, C, D. These are the elements of the base set. These will be the vertices of the graph representation of R. So you can see A, B, C, D. Now you can see what are the edges. C related to A. Next, A related to B. Next, A related to C. A related to C. Next, B related to C. D related to C. C related to D. Okay, this is your relation for R, remember. Okay. Sorry, this is the graph representation for R. Now, what we need to do? Now we need to make the graph representation for S. Okay. So you can see A, B, C, D. Now I'm making the graph representation for S. Okay, remember one thing, that in S, I can say that X will be related to Y in S. Okay, this is X. This will be related to Y in S. In S. When can I say X will be related to Y in S? When there is some Z such that X is related to Z in R. Okay, remember, X is related to Z in R, in R, and and Z is related to Y in R. Okay, this is given in the question. This is the definition of relation S. You can see that. You can see here the pair XY is in S, means in this relation S, X will be related to Y if and only if there exists a Z, there exists an element Z such that XZ is related, X is XZ, or I can say X is related to Z in R and Z is related to Y in R. Okay, is this clear? So now you can easily find the graph representation for S. You can see, let's see from A what will be the edges. Okay, from A point of view, you can see that A is related to B, B related to C, so A will be related to C. Yes or no? First, you focus from A point of view. Now you are standing at A. So you notice A related to B, B related to C. So I can say that A will be related to C in S. Next, you can notice one more thing, that A is related to C, C related to A. So A will be related to A. Yes or no? Did you notice that A is related to A in R? Sorry, A is related to C in R. A is related to C in R. Then C is related to A in R. So what I can say, that A will be related to A in S. Okay, do you agree with me? Very simple. Now, is there any other A's from A? From A point of view, I am thinking, you can see, okay, this direction we have already covered. A related to C, C related to D, so A will be related to D. Okay, yes or no? So that's it. We have completed all the we have completed all the edges from A. Okay, from A, these will be the edges. You can notice that there will be no edge from A to B in S. In S, there will be no edge from A to B, because you can see there is no immediate person through which A is related to B. Okay, you can see A is related to C, but C is not related to B. So there is no intermediate. There is no intermediate person through which A is related to B. Okay, is this clear? Very simple. Now, what about from the B point of view? Now you are standing at B. You can see B related to C, C related to D, so B will be related to D. B related to C, C related to A, so B will be related to A. That's it, nothing else. Yes or no? What about from the C point of view? Now I am standing at C. From the C point of view, you can see C related to A related to B, so C will be related to B. C related to A related to C, so C will be related to C. C related to D related to C, so C will be related to C. Okay. Now you can see that from C to A there will be no edge, because C is not related to A through intermediate person. Yes or no? C is not related to A through intermediate person. So that is the reason in this relation S there is no edge from C to A. Also, C is not related to D through an intermediate person. Okay, yes or no? So from C to D also there is no edge. Okay, now you are standing where? Now I am standing at D. Okay, so you can see that D related to C, D related to C, C related to D. So there is a self loop on D. D related to C, C related to A. So you can see there will be A's like this. Okay, that's it, nothing else. Okay, so finally, this is your relation S. Now you can calculate what is the number of edges in this graph representation. That will be the size of S. Okay, so the size of S, that will be how many edges are there, how many arrows are there in this graph representation. So the answer will be, you can see, just calculate the outgoing edges. You can see from A, 3 outgoing edges are there. Okay, so I can say 3 plus. From B, 2 outgoing edges are there. Okay, from C, 2 outgoing edges are there. From D, 2 outgoing edges are there. Yes or no? I am calculating the outgoing edges. Okay, so finally the answer will be 3 plus 2 plus 2. That will be 9. Okay, so for this question, the answer will be 9. Okay, so this is a very simple question. I hope you understood. Remember, graph representation is one way to solve this question. Of course, there are other ways also, but this graph representation is very useful. You can use it for many questions based on relations in discrete mathematics. Okay, I hope you understood. Let's solve this question from discrete mathematics graph theory. A graph consists of finite set of vertices and edges between some pair of vertices. Unordered edges means we have undirected graph. The graphs in this question have no loops. There is no self loop. Means what is a loop? An edge between a vertex and itself. So there are no self loops. Or multi edges means we don't have duplicate edges between same pair of vertices. We don't have more than one edges. A vertex V in the graph is said to be global vertex if it is adjacent to every other vertex in the graph. Okay, so you can see a vertex V in the graph is said to be global vertex if there is an edge between V and every other vertex in the graph. Okay, if the vertex V is adjacent to every other vertex in the graph, then it will be called global vertex. Okay, a graph is constructed as follows. We are constructing a graph, undirected graph. We are constructing first, its vertex set is basically V1 to V10. Okay, means there are total 10 vertices in this graph. So you can see its vertex set is assigned to be the set V1 to V10. Next, what we do? Between each pair of distinct vertices, we are adding an edge with probability half, 1 by 2. Now the question is asking, let the expected number of global vertices in the graph. Let the expected number of global vertices in the graph G be n. Then what is the value of n into 2 power 10? Okay, this is the question. So let's solve it. You can see we have total 10 vertices in the graph. Now, when can I say a vertex is global vertex? You can see the vertex set, that is V1, that is V1, V2, V3, and so on, V10. Okay, this is the vertex set. Now the question is saying that a vertex V is global vertex. When can I say this vertex V? This vertex V is global vertex. This vertex V will be global vertex if it is adjacent to every other vertex like V2 also, V3 also, V4 also, and so on, V10 also. Okay. If it is adjacent to every other vertex, then this vertex V, for example, this vertex V1, okay, let's assume this vertex V1 will be called global vertex if it is adjacent to every other vertex. Okay. Now, you just tell me a very simple point. You can see that this edge has probability 1 by 2. This edge has probability 1 by 2. This edge has probability 1 by 2, 1 by 2, 1 by 2, like that. So tell me, what is the probability that this vertex V1 will be a global vertex? Tell me what is the probability? What is the probability? Probability that vertex V1 is a global vertex. Can anyone tell me? This vertex V1 is a global vertex. What will be the probability? What is the probability that this vertex V1 will be a global vertex? If V1 should be a global vertex, then we should have this edge and this edge and this edge and this edge and so on. Yes or no? We must have this edge and we must have this edge and we must have this edge and so on. So the probability that this vertex V1 will be a global vertex, that is basically 1 by 2 power 9. Yes or no? Okay, it will be like 1 by 2 into 1 by 2 into and so on. 1 by 2. Total 9 times. Okay, so you can see 1 by 2 power 9. 1 by 2 power 9. This is the probability that vertex V1 will be a global vertex. Okay, is this clear? So remember, this same probability will be for all the other vertices to become a global vertex. Do you agree with me? So I can say that for any vertex, remember, for V1 also, this we have this probability. If V1 should be a global vertex, then you can see this is the probability. By this probability, this V1 will be a global vertex. This V2 will be a global vertex by the same probability. Okay. V3 will be a global vertex by the same probability, and V10 will be a global vertex by the same probability. Means probability that V10 will be a global vertex, that is also 1 by 2 power 9. Yes or no? Is this clear? Basically, here I can write that probability that any Vi is a global vertex is a global vertex. Okay, that probability is basically 1 by 2 power 9. Okay, or I can say it's like 1 by 2 power 9, like that. Okay, is this clear? So you tell me, by 1 by 2 power 9 probability, this is global vertex. By 1 by 2 power 9 probability, this is global vertex. By this same probability, these are the global vertices. So what will be the expected number of global vertices? What is the expected number of global vertices? Tell me, what will be the expected number of global vertices? So you can do the summation here, and the answer will be 10 divided by 2 power 9. Okay, yes or no? It's like 1 by 2 power 9 plus 1 by 2 power 9 and so on, 1 by 2 power 9. So that is 10 divided by 2 power 9. Okay, is this clear? Very simple point, remember. By this probability, 1 by 2 power 9, by this probability, this V1 is a global vertex by this probability. This V2 is a global vertex by this probability, and so on. So what is the expected number of global vertices? That will be, you can just do the addition summation here, and that will be 10 divided by 2 power 9. And the question is asking what? The question is simply asking what is n into 2 power 10. So already we got n, that is 10 divided by 2 power 9. So what will be this value? If you multiply by 2 power 10, then it will become 20. Okay, you can see if you multiply this by 2 power 10, then it will become 20. So the expected number of global vertices is actually this. Okay, but this value is 20. Okay, don't think that expected number of global vertices is 20. Already we have 10 vertices. Don't think that expected number of global vertices is 20. This is expected number of global vertices. This is expected number of global vertices. Okay, I hope you understood this. So very simple question. It is clear? Let me know. Let's solve this question from compiler design based on LA-LR1 parsing technique. This is the most beautiful question, I think, one of the most beautiful question in this test. The question is asking, in the context of LA-LR1 parsing technique, consider the following statements about the type of items used and the automaton on which this method is based. Now there are some statements given. LA-LR1 method is LA-LR1 method uses LR0 items and it is based on LR0 automaton. LA-LR1 method uses LR1 items and it is based on LR0 automaton. Basically, the question is asking that LA-LR1 parsing technique, or I can say LA-LR1 method, it uses which items, LR0 items or LR1 items. Also, the question is asking that this LA-LR1 method, it is based on which automaton, LR0 or LR1. Now let me tell you, the answer will be that LA-LR1 parsing technique, it uses LR1 items, but it is based on LR0 automaton. So for this question, the answer will be actually option B. Let me tell you, the complete explanation I provided you in this video. You can see on the Gate Overflow website, under this question, I provided this lecture, the complete lecture on LA-LR1 I provided. In this lecture, you can just watch the first 1 hour. Okay, you can watch the complete lecture also if you want, but the point is, the first 1 hour if you watch, then you will get complete understanding of LA-LR1 parsing technique. Okay, let me tell you one thing here, one interesting thing here. Of course, if you watch this lecture, then it will become more clear. Okay, but let me tell you one interesting thing, that see, for any grammar, how to create LA-LR1 automaton? For any given grammar, for a grammar, for a grammar G, how to create LA-LR1 automaton? How to create LA-LR1 automaton? How to create it? For any grammar G, how to create LA-LR1 automaton? Now, the method that we use, most of the people, or I can say the humans, you, I, most of the time, the method that we use, what is that? That is, first we create the LR1 automaton, then we merge the states with the same core and we get LA-LR1 automaton. Yes or no? So you can see this is the method 1. There is this method. This method is saying that what you do, first you create LR1 automaton. Okay, first you create LR1 automaton, you create. Okay, and then first create LR1 automaton, and then what you do, then you merge states with the same core. You merge states with the same core. States with the same core. Okay, what is core? Core is the set of first components. Okay, is this clear? This core, this is the set of first components. Because you already know that in this LR1 automaton, we use LR1 items. Every LR1 item has two components. The first component is LR0 item, and the second component is look ahead. Yes or no? So remember, the set of first components, that is called core. So if two states have the same core, two or more states have the same core, then we can merge them. Yes or no? This is the method we can use to create LALR1 automaton. But let me tell you, there is another method. There is another method which is efficient for machines. This is efficient for humans. But let me tell you, this method is not used by the machines. In practical life, in the compilers, if you want to create LALR1 automaton, if you want to create LALR1 parsing table, then this method is not used in the compilers. Compilers don't use this method. Humans use this method. You, I, we use this method. But this is not efficient from the machine point of view. You can see there is method number 2, which is efficient from the machine point of view, but it is hectic from human point of view. Okay, so let me tell you this method number 2. It is in this method number 2, first we create LR0 automaton. First we create LR0 automaton for this grammar. First we create LR0 automaton for grammar G. Okay, for this grammar, first you create the LR0 automaton. This is what you create. And then what you do, then you attach the look ahead. Okay, basically you are creating the LR0 automaton. So LR0 automaton has LR0 items, but this LALR1 automaton, or I can say the LALR1 parsing technique, it uses LR1 items. So what we will do, we will attach the LR1 look aheads. So you can see in this LR0 automaton, what you do, you attach the LR1 look aheads. The LR1 look aheads. Okay, if you do this, then you will get LALR1 automaton. Okay, now let me tell you one more thing. Actually, LR0 automaton creation, this is very easy. You can do it very easily from the grammar. How to create LR0 automaton, that you already know. Okay, but let me tell you, this attaching the LR1 look aheads. Okay, in this LR0 automaton, with every LR0 item, we are finding the correct set of LR1 look aheads. Finding this correct set of LR1 look aheads to attach with the LR0 items, this is actually a hectic procedure. Okay, there is a process. Okay, there is something called propagate and all these things. But the point is, this is given in the standard books, in the standard resources, but we don't have to worry about it. But from this method number 2, one question you can answer. What is that? From this method number 2, you can answer this question, that your LALR1 automaton, this is basically LR0 automaton plus LR1 look aheads. Okay, it's like this. To create LALR1 automaton, you are taking the LR0 automaton and you are taking the LR1 look ahead. Means good things from here, good things from here. What is good thing in the LR0 automaton? Less number of states. Yes or no? LR0 automaton has less number of states. LR1 automaton has high number of states, a large number of states. So it is a good thing that we want less number of states. So we take the LR0 automaton. And in the LR1 automaton, what are the good things? The number of states is not a good thing. So what is the good thing in the LR1 automaton? The look aheads. These are the good thing in the LR1 automaton. So you take the LR1 look aheads, you take the LR0 automaton, you attach them, and you got your LALR1 automaton. Okay, is this clear? So remember, finally I can say that for this question, the answer will be what? The answer will be that the LALR1 method, LALR1 parsing technique uses LR1 items, but it is based on LR0 automaton. And let me tell you, this question is taken from Ullman and Stanford. Okay, if you want, to know more about it, if you want to understand this complete LALR1 parsing technique, this complete LALR1, if you want to understand in a crystal clear way, clear, correct, and complete understanding, if you want, then you can watch this lecture, or you can watch the first hour of this lecture, or you can watch the complete lecture. Okay, must watch it. It will tell you, it will give you the complete understanding of LALR1 parsing technique. I hope you understood. Okay, so for this question, the answer will be option B. Let's solve this question from theory of computation. Which of the following statements is or are true? DFA stands for deterministic finite automaton. NFA stands for non-deterministic finite automaton. The four statements that are given. So let's see. For every DFA or NFA, LM equal to sigma star. We have a DFA or NFA M over sigma. This is the alphabet. Then the language will be sigma star if and only if each reachable state, every reachable state is an accept state. Every reachable state is accept state. Actually, this statement is true for DFA, but it is not true for NFA. For NFA, if some reachable state is not accept state, then also the language can be sigma star. Very easy example I can give you. Notice, consider this sigma. Let's consider this sigma equal to A. Now what to do? You can see that. Let's make a NFA. I am making a NFA. This is the initial state. On A, I am going here. On A, I am going here also. Okay. Notice. Now you notice that this is a reachable state. From the start state, you can reach here. Yes or no? Look at this. This is a reachable state. This is a reachable state, but still you can see that it is not, it is non-final. Yes or no? It is reachable state. It is non-final state, but still you can see what the language of this NFA. This is NFA. This is NFAM. Okay, so you can see that what are the language of this NFA? That is basically sigma star. Yes or no? Is this point clear? So remember this statement that for every NFA, language is sigma star if and only if every reachable state is accept state. This statement is actually true for DFA, but it is not true for NFA. Okay, is this point clear? So overall, this statement is basically false. Okay, so let me tell you, this statement is actually true. So what will be the true statement? It will be like this. For DFA, M, what you can say? You can say that LM equal to sigma star. The language of M will be sigma star if and only if and only if every reachable state is final state. If and only if every reachable state is final state. Okay. But remember, for NFA, this if and only if is actually not true. So for NFA, can I say that? Can I say this direction is true? Can I say this direction is true? Let me know. See, just let me know this point. Can I say if you have, for NFA, I'm asking, you just tell me which direction is correct. For NFA, you let me know. If the language is sigma star, then does it imply every reachable state is final? Tell me, every reachable state final? Tell me, if the language is sigma star, does it imply that every reachable state is final? No, we have already seen the counter example. Here the language is sigma star, but this reachable state is not final. Okay. Tell me one more thing. If every reachable state is final, in NFA, if every reachable state is final, then can I say the language will be sigma star? Simple question I'm asking, you tell me the answer. This is first, this is second. Tell me, can you tell me the answer now? If every reachable state is final, then can I say that language will be sigma star? This is also not true. Okay, for NFA, this is also not true. Why this is not true? Consider this. Consider NFAN. Let's consider this NFAN. I'm making every reachable state final. You can see your alphabet is A. What are the language? Notice every reachable state is final, but what are the language here? The language is basically epsilon comma A, not A star, not sigma star. Okay, is this point clear? So notice one thing, every reachable state is final. here here every reachable state, here every reachable state is final. Okay, here every reachable state is final, but remember, still you can see that the language is not sigma star. Okay, is this clear? For NFA, both the directions are actually false. If the language is sigma star, it does not mean that every reachable state will be final. If every reachable state is final, it does not mean that language will be sigma star. So for NFA, both the directions are false. For DFA, both the directions are true. Okay, is this clear? Very simple. So you can see statement A for DFA or NFA, language is sigma star if and only if every reachable state is accept state. This statement is actually false because of NFA. For DFA, this statement is actually true, but for NFA, actually both the sides are actually false. Okay, let's see the next. For all set A comma B, if A and B are non-regular, then their intersection will be non-regular. This statement is also false. I can give you two non-regular languages whose intersection will be actually regular. Okay, let's consider non-regular languages. You can actually consider any non-regular language. What you do, you take any non-regular language L. What to do? You take any non-regular language L. We already know that we already know that L complement also will be non-regular. Do do you know this? That if you take any non-regular language, then its complement also will be non-regular. Can you prove it? We already know that L complement is also non-regular. Okay. So what are the proof? Of course, let's see the proof quickly. The proof is like this. If your language is non-regular, okay, L is non-regular. Now we want to prove, I want to prove that L complement is also non-regular. For contradiction, let me assume that L complement is regular. For contradiction, okay. Actually, I need to prove that L complement is also non-regular. But for a contradiction, for a moment, let me assume. For contradiction, assume. I am making an assumption. Assume that L complement is regular. Okay. Now what will happen? If L complement is regular, then regular complement will be regular. That we already know. Yes or no? Notice, if L complement is regular, then the complement of regular will be regular. So if I complement it again, then that also will be regular. Okay. L complement again complement, that will be L. So basically I got L regular. Now here I got a contradiction. Yes or no? Here I got a contradiction. Did you notice? I got contradiction. So if I got a contradiction, then definitely my assumption was wrong. Okay. My assumption was wrong. What was my assumption? My assumption was my assumption was that L complement is regular. So that assumption is wrong. It means L complement is non-regular. This is the proof. Okay, yes or no? I hope you understood this point. So this is the proof. So finally, I can say that if you take any non-regular language L, you take any non-regular language L, now you can see that L complement is also non-regular. Now what you do? Now you take their intersection. What will be their intersection? Can you tell me? You can see this is non-regular. You can see this is non-regular. I am taking their intersection. What will be their intersection? That will be phi. L comma L complement. They cannot have anything in common. Yes or no? L comma L complement. Their intersection is phi, and phi is actually regular. So remember, non-regular languages are not closed under intersection operation. Okay, is this clear? Means non-regular intersection non-regular may or may not be regular. This is the conclusion, that if you have non-regular intersection non-regular, the intersection of two non-regular languages, non-regular language 1, non-regular language 2, the intersection of two non-regular languages that may or may not be regular, that may or may not be non-regular. Okay, that may be non-regular. Remember, for example, if you take both same, you can take. Okay, for example, consider I'm giving you another. Consider this L1. This is a power n, b power a power n, b power n. Okay, n greater than equal to 0. This is famous non-regular language. You already know this. This is a non-regular language. Okay. Now consider L2, that is a power 2n, b power 2n, where n greater than equal to 0. Yes, this is also non-regular. But what about their intersection? L1 intersection L2, that will be same as L2, and that is non-regular. Okay. So remember, very simple point that the for the non-regular languages, I can say their intersection may or may not be non-regular. Similarly, for the union, so let me write it. The closure properties. Similarly, you can prove for other operations, closure properties for non-regular languages. When I say non-regular language means in our base set we have all the languages which are not regular. Okay. So for the non-regular languages, remember, I am discussing closure properties of non-regular languages. I am not discussing closure properties of CFLs. I am not discussing closure properties of RE languages. I am not discussing closure properties of CSLs. Don't come to me and say that, sir, this CSL, these are also like non-regular. So how it can happen like this? Please understand, when you discuss the closure properties of CSL, then our base set has all the CSL languages. When we discuss the closure properties of non-regular languages, then our base set has all the non-regular languages. Every language which is not regular, that is in our base set. So all the CFLs which are not regular, all the CSLs which are not regular, all the RE languages which are not regular, all the non-RE languages, basically every language that is not regular, that is in our base set. Okay, is this clear? So remember, the closure properties of non-regular languages will be like this. If you have a non-regular language, N1 intersection non-regular language L2, then remember the result may or may not be regular. The result may or may not be regular. Okay. The same thing will happen for union, for set difference. Okay. So basically the same thing will happen. I can say N1, N2, N1, N2. The same thing will happen for concatenation. N1 concatenation N2. For the concatenation also, the same thing will happen. So in all these situations, you can say that the result may or may not be regular. Okay. But one more thing, we have already seen that for the non-regular language, the complement will be non-regular. The proof we have already seen by contradiction. The non-regular language complement will definitely be a non-regular language. Okay. And you can see, so for example, if you have non-regular language 1, then its complement will be non-regular language 2. And notice one more thing, that for the non-regular language, the reverse, that also will be non-regular. Okay, this also you can prove with the contradiction. Means you take a non-regular language, for contradiction, assume that its reverse is regular. Then again, if you do reverse, then you should get regular, but actually it is non-regular. So there is a contradiction. Okay, basically this we have already proven by contradiction. Similarly, by contradiction, you can prove this also. I hope you understood these points. Okay. Now let's see the next question. Now let's see the next option. Here you can see that for set A comma B, if A comma B are non-regular, then their intersection is also non-regular. This statement is false. What about option C? For all set L is regular if and only if L star is regular. This statement, this is also false. Okay, C. What about statement C? We are saying that if L regular, if L regular, then L star will be regular. This is true. This is true. There is no problem here. If L regular, then L star will be regular. This is true. Okay, but if L star regular, if L star is regular, then can I say L will be regular? This is actually not necessary. Okay, means if L star is regular, if L star is regular, then L may or may not be regular. L may or may not be regular. Okay, example. Let's see example. Example will be like this. You consider L equal to a power prime. Okay, a power p, where p is prime. So what is L? L is basically a power 2, a power 3, a power 4. Sorry, not a power 4, prime. Okay, a power 5, a power 7, a power 11, and so on. Okay. Of course, you already know that this a power prime, this L, this is non-regular. Okay, this language is CSL but not regular. Okay, this is actually CSL but not CFL. So this language, it is CSL but not CFL. So this is not regular also. Okay. Now you notice what is L star. Can you find what is L star? What will be L star? You can see that L star will definitely contain epsilon. L star will contain all these strings like a power prime. L star will also contain a power composite. Okay, because from these prime numbers you can create all the composite numbers. Yes or no? There is a theorem, right? Fundamental theorem of mathematics. What is that? That any composite number, or I can say basically any number that is greater than or equal to 2, I can write it as product of powers of prime numbers. Yes or no? Okay, so basically the prime division, prime factorization, yes or no? So for any integer greater than equal to 2, we can do prime factorization. So you can do that, prime factorization. So you can see that using all these prime numbers, I can create all the composite also. So basically, except A, I got everything. What I got? I got sigma star minus A. Sigma star minus A. This is what I got. Okay, of course, this is regular. Okay, this is a regular. I got all the strings except A. So you can see that L star is actually regular, but L is not regular. Okay, is this point clear? So remember, if L is regular, then L star will be regular, correct? If L star is regular, then L will be regular. This is not necessary. Okay, is this clear? So this option C, that is also false. Now let's see. For all set L, L is regular if and only if complement of L is regular. Yes, this statement is true. If L regular, then L complement will be regular. If L complement is regular, then you can again do the complement. For a regular language, the complement will be regular. So you can see you got regular. So a language is regular if and only if its complement is regular. A language is regular if and only if its complement is regular. Okay, so for this question, the answer will be option D. Only option D will be correct. This is actually MSQ question, but only option D will be correct. I hope you understood this. The complete analysis of this question, I hope you understood. Very simple question, but a beautiful question. Some small things you have to take care. Okay. Before we see the remaining questions, let me tell you that if you want to attempt all the Go classes mock test, including the All India mock test AIMTs, then you can enroll in Go classes full length mock test package. This full length mock test package, this we have launched, and you can enroll this. You can see for gate CS, for gate DA, for gate CS plus DA combo, If you want to attempt all the full length mock test of Go classes, including all the All India mock tests, then this full length mock test package you can enroll. You can visit the Go classes website. On the Go classes website, you will find this button, this test series button on the home page. This button you click, and then you can find this full length mock test package. Okay, this full length mock test package you can find. You can click this and you can enroll in Gate CS mock test, full length mock test, Gate DA full length mock test, Gate CS plus DA combo full length mock test. Remember, in the Gate CS mock test package, full length mock test package, you will get total 20 full length mock test, including all the AIMTs. In Gate DA full length mock test package, you will get total 15 full length mock test, including AIMTs. And in this combo, CS plus DA combo, in this combo mock test package, you will get 35 full length mock test, including the AIMTs. Okay, very simple. I hope you understood. Now let's move on. Let's solve this question from theory of computation based on decidability. Which of the following problems is or are decidable? The question is saying that which of the following problems is or are decidable. First, let's see option C, D. Given a DFA, does it accept only finitely many inputs? Means given a DFA, is the language finite? So this is finiteness problem for DFA, finiteness problem for regular languages, that is decidable. These are standard results. For DFA, the finiteness problem means for a given DFA, the language is finite or not. The finiteness problem, the infiniteness problem, these are decidable for DFA for regular languages. For PDA also, this finiteness problem, or I can say infiniteness problem, these are decidable for PDA, for CFLs also. Okay, so you can see that these two problems, these are famous decidable problems, standard decidable problems. In our Go classes lectures, we have also seen the proof also. Okay, like for the regular languages, the finiteness problem, the infiniteness problem, why that is decidable. For PDA, why it is decidable. So the proof also we have seen in our Go classes lectures, but these are standard decidable problems, so I don't think you will face any difficulty in option C, D. Okay, now let's see the option A, B. These are really interesting options. In the option A, we have given a context-free language L and a regular language R, is L subset of R? So is it decidable that we can decide basically is L subset of R? Similarly, in this option B, we have given a context-free language L, regular language R. Can we decide this, that is R subset of L? So let's see here. Let me tell you, you can apply the definition of subset. Notice a very small thing, that when can I say A is subset of B? A is a subset of B if and only if, you can see this is A, this is subset of B. A is subset of B if and only if A minus B is equal to phi. Yes or no? This is the definition of subset. Okay, A is subset of B if and only if A minus B, from A if you remove B, then you should get phi. Now what is A minus B? A minus B I can write as A intersection B complement. So this is equal to phi. Okay, overall basically I can say that A is subset of B if and only if A intersection B complement is equal to phi. Okay, yes or no? Very simple. Now let's see the option A. Let me see option A. Option A is saying that given L is CFL, R is regular. Okay, two languages are given to us. Now the question is asking, is L subset of R? Is L subset of R? Okay, so very simple. Is L subset of R? Means we are asking, is this L, is it subset of R? Okay, this is what the question is asking. So very simple point. You already know that L is subset of R if and only if L minus R that is equal to phi. Yes or no? L is subset of R if and only if L minus R that should be phi. Okay, this same thing I can write that L intersection R complement is equal to phi. Now, regular language complement that is regular, yes or no? So I can say it is like CFL intersection regular. CFL intersection regular is phi. What is CFL intersection regular? That is basically CFL. CFL is equal to phi. So the complete question has now become that is this CFL equal to phi? Okay, not the CFLL, a new CFL. Okay, a new CFL you have got. Basically, the complete question now the complete question has become, is this CFL L2? Okay, some L2 you got. Okay, of course, here CFL intersection regular, that will be a CFL, some different CFL. But the complete question has become that is this CFL equal to phi? And remember, for CFLs, the emptiness problem that is decidable. Okay, this is emptiness problem for CFLs. This is emptiness. This is emptiness problem for CFLs. Okay, and emptiness problem for CFLs that is decidable. These are standard results, but just in a clever way, you have to think. Okay, you can see the question was basically asking you, is L subset of R? So in a clever way, you have to think that basically this question I can reduce to this question. Yes or no? We are replacing this question with the another question that a CFL is phi or not. Okay, and for the CFLs, the emptiness problem is actually decidable. For the PDA, it is decidable. We can decide whether the language of the PDA is empty or not. Okay, is this clear? So I can say that this option A, this is also decidable. I hope you understood. Now let's see the option B. That is interesting. Option B is saying that you have context free language L, regular language R. Is R subset of L? Okay, let's see this. Is R subset of L? So you can see option B. Option B is saying that L is a CFL, R is a regular. Okay. Now, L is a CFL language, R is a regular language. And now the question is asking, is R subset of L? Okay. Now, let me give you two logic here. One will be the formal proof, another will be just a simple logic. So you can see that is R subset of L? You already know that. R is subset of L if and only if you can apply the definition, if and only if R minus L is equal to phi. Yes or no? Okay, R minus L is equal to phi. That simply I can write it R intersection L complement is phi. Now notice CFL complement. Actually, CFL complement, let me tell you, this complement of CFL will be a CFL or not, that itself is not decidable. Okay, for a given CFL, sorry for that, we are saying, yes, we are saying that for a given CFL, the complement will be CFL or not, that itself is not decidable. If you give me a CFL and if you ask me the complement of this CFL is CFL or not, that itself is not decidable, because complement of CFL may or may not be CFL. Of course, that is not a proof. Closure property is not a proof. Using closure property, I can say that the complement of CFL may or may not be CFL. But there is a complicated proof. We don't go into that. But the point is, for a given CFL, it is not decidable that the complement will be CFL or not. Okay, is this clear? Here you can see that this L complement, this itself may or may not be CFL. Okay, also we cannot decide whether this is CFL or not. Okay, so let me tell you, undecidable to decide if it is CFL or not. Okay, this is CFL or not is also undecidable. Is also undecidable. Okay, so overall the point is basically from here you are getting some idea that this problem this problem is undecidable. Okay, because see, definitely this will be CSL, because every CFL is CSL and the complement of CSL is CSL. Okay, so you can see that definitely this is, I can say this is definitely CSL. And what is regular intersection CSL? The regular intersection CSL, this is basically CSL. Now a CSL is phi. Emptiness problem for CSL is phi. Emptiness problem for CSL, that is undecidable. Okay, that is undecidable. So overall, actually, this problem, this is undecidable. Of course, this is not a formal proof. I did not give you the formal proof, but let me give you the formal proof also, because that is also very interesting. You will understand and you will appreciate more. Okay. So let me give you the formal proof. Notice, we already know that the universality problem for CFLs, that is undecidable. Yes or no? Do you know this? We know the universality problem. Universality problem. What is the universality problem? The universality problem means sigma star problem. Okay, means sigma star problem. Means a given CFL language is sigma star or not. Okay, so universality problem for CFLs is undecidable. Okay, the universality problem for CFLs is undecidable. This is a standard result. You must be knowing this. Okay, this is undecidable. Means given a CFL, is it sigma star? That is undecidable. Okay, is this clear? So you can see that given a CFL L, given a CFL L is L sigma star, or I can say given a PDA is the language sigma star. So this is actually undecidable. Okay, is this clear? Given a language, given a CFL, given a PDA is the language sigma star, this is undecidable. This is undecidable. Okay. Now what you do? For a moment, for a moment you assume that this is decidable. Okay, for a moment, let's assume this is decidable. Now, one more thing, let me just tell you. So this is note number one. Okay, this is note number one. Let's see a note two also. What is that? You just tell me a simple point. If sigma star is subset of L, what can you say about L? If sigma star is subset of L, what can you say about L? Every language is subset of sigma star. So if sigma star is subset of L, then definitely L is sigma star. Yes or no? Do you agree with me? That if sigma star is subset of L, then L itself will be sigma star. Okay, very simple. Now let's come back to this question. What I'm saying? I'm saying that assume this is decidable. Okay, for a moment, assume it is decidable. Now, a story I will tell you. Okay, this story you try to understand. Assume this is decidable. Means there is some person. Okay, assume this problem is decidable. So there is some person who is saying that I can decide it. Okay, there is some magical godman. Okay, let's call it godman. So there is godman here who is claiming that I can decide this problem. Okay, basically this godman is saying I can decide. I can decide. I can decide if R is subset of L or not. Okay, means you give me regular language, you give me CFL, I will tell you yes or no. Okay, there is a godman. So let's assume that this problem is decidable by this godman. Okay, by this godman. By this godman. Okay. So now you can see what this Godman is basically saying. This Godman is saying that you give this Godman a CFL you give, okay, a CFL you give, and a regular language you give, okay, a regular language you give. And this Godman, what it will do? You give these inputs, okay, and what this Godman will give you? It will give you the output, yes or no, yes or no. Okay, is this clear? Yes R is subset of L. Yes means yes R is subset of L, and no means R is not subset of L. Okay, is this clear? So this type of Godman is there. Let's assume, of course, this we are assuming. Okay, now you will see there will be a contradiction. So our assumption will be false. I will create a contradiction. Right now, I am just assuming that this problem is decidable. So this is decidable by a Godman. Okay, this Godman can decide, means you give this Godman input CFL comma regular language, you give a regular language, you give a CFL, and this person, he can give you the output yes or no. Okay, is this clear? So now what is the problem then what is the problem? How to bring contradiction? Now to bring contradiction, what I will do, I will give a CFL, that is fine, but I will give a sigma star. No, now notice one thing. For contradiction, what I will create? Now I heard about this Godman. I heard about claim of this Godman. Okay. I heard about claim of this Godman. Okay. Now what I will do to contradict him, or I can say that for contradiction, what I will to contradict, for contradiction, to prove him false, or I can say for contradiction, what I will do? For contradiction, I give a CFL input, I give a CFL L, and I give R equal to sigma star. Okay, what I will do? I will give R equal to sigma star. Now notice, already we know that for a CFL, is it equal to sigma star? That is actually undecidable. That I already know. Yes or no? We already know that for a given CFL L, is it sigma star? That is undecidable. Okay, the universality problem for CFL, that is undecidable. Okay, so now what I'm doing to this Godman, I'm giving a CFL L and R equal to sigma star. This is what I'm giving. Okay, so let me give these inputs. I'm giving a CFL L, a regular language, and R equal to sigma star. Okay. Yes, sigma star is a regular language, so I can give. As soon as I give these two, now this Godman is saying that I will definitely give you answer yes or no. I will not go into infinite loop. Okay. I will definitely give you answer yes or no. So remember these inputs you have given, and now the output you will get. Now notice, if the output is yes, then also we have decided the universality problem. If the output is no, then also we have decided the universality problem. Okay, if this Godman says, if the output is, let's assume yes, if the Godman says the output is yes, yes means R is a subset of L. Then notice one thing, if this Godman says that the answer is yes, yes means R is subset of L, what it actually means? It would mean, it would mean what? Just let me know. It would mean, tell me what it would mean. It would mean that sigma star is subset of L, and that will mean L is sigma star. Yes or no? So this Godman, what this Godman has done? This Godman has decided universality problem for CFLs. This Godman has decided that given a CFL, is the language sigma star or not? Yes or no? Of course, that is problematic. Yes or no? One more thing. If this Godman gives you answer no, if this Godman gives you answer no, then what it would mean? The Godman says the answer is no means R is not subset of L. Then what it would mean? It would mean that sigma star is not subset of L. It means L is not sigma star. Okay, please understand what is happening here. It's happening that if this Godman exists, let's assume, means if this problem is decidable, then what you can do? Then in the regular language, you can always give sigma star and you can always decide the universality problem for CFLs. Did you understand what is happening here? You can see if notice if decider exists, decider M, let's assume if decider M exists to decide if R is subset of L or not, if R is subset of L or not. Okay, you can see if a decider M exists to decide if R is subset of L or not, then 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 what we can do? Then we can decide then we can decide then we can decide universality problem for CFLs. Yes or no? Then we can decide universality problem. You can decide universality problem for CFLs L by giving by giving by giving L comma sigma star to this machine M. Okay, is this clear? Are you getting my point? So remember, if decider M exists to decide whether a regular language R is subset of a CFL L or not. Okay, so to decide this, if decider M exists, then what we can do? Then we can decide the universality problem for CFLs. The universality problem for CFLs we can decide by giving L comma sigma star to M. Okay, but we already know that this universality problem for CFL is undecidable. So there is a contradiction here. Yes or no? So it would make existence of decider M. I can say existence of decider M makes universality sigma star problem for CFLs decidable. Yes or no? The existence of this type of decider M will make the universality problem, the sigma star problem for CFLs decidable, which is a contradiction. Because we already know it is undecidable, which is a contradiction. Okay, I hope you understood. So finally, I can say that no such decider M exists for problem is R subset of L. Okay, is this clear? So there is no such decider exist. I hope you understood. Okay, basically what we have done, let me tell you what we have done. This is what we have done, that the universality problem, if you notice what we have done, the universality problem of CFLs, to solve this problem, we can use this decider. Of course, this decider does not exist, but by any chance, if this decider, let's assume, existed, okay, let's assume if such a decider existed, then to solve the universality problem, we can use this decider. Means basically we can reduce this universality problem of CFLs to this problem. Which problem? Is R subset of L? Is R subset of L. Okay, so this reduction we have done, we can do. This reduction we can do. Okay, how to do this reduction? Very simple. Very simple. How to do this reduction? The reduction is actually very simple. L will be as it is. Okay, L will be as it is. And in R, I can put sigma star. Okay, L as it is. L as it is. And what I can do? In R, I can put sigma star. Okay, yes or no? In R, I can put sigma star. So this is how I can do the reduction. So remember, if such decider existed, it does not exist, but for contradiction, if this type of decider existed, then we can reduce this universality problem to this problem. Okay, this reduction we can do from universality problem to this problem. So if this problem is decidable, then definitely this problem will also become decidable. Okay, so you can see that if this problem becomes decidable, if decidable, okay, if this problem is decidable, then this problem will also become decidable. Okay, of course, this is a contradiction. Okay, you got a contradiction. We got contradiction. Okay, that's it. I hope you understood. So finally, remember, for this question, this is actually undecidable. Okay, the question is asking which is decidable, so these are actually correct. Okay, I hope you understood this. Very simple. The complete analysis of this question, I hope you understood. Okay, very simple. So this is an interesting question. I hope you understood. Let's solve this question from theory of computation. Consider the following context-free grammar G over alphabet sigma a comma b. This context-free grammar is given to us. Let GA denote the grammar obtained from G by deleting the variable a and all its related productions. We are deleting the variable a from the grammar, and of course all its productions also will be gone because you are deleting this non-terminal a from the grammar. So this non-terminal a and all its productions will be gone. Similarly, GB is also defined. Means GB means from this grammar you delete the non-terminal b and all its productions, then you will get this GB, this grammar you will get. Okay. Now some options are there. Which of the following is or are true? G is ambiguous. What do you think? G is ambiguous or not? Actually, in this G, if you notice one thing, in this G, if you apply the substitution rule, if you apply the substitution rule, I am checking for option A. Option A I am checking. So if you apply the substitution rule, then what I will get? I will get something like S going to A. You can see this B will go to SB. Okay, whenever I will go to B, then this B will go to SB. So like this. Next, you can see this A, whenever I go to A, this A will go to AS, this AB. Okay. Did you notice that basically here you can easily notice the ambiguity? Okay, I am basically saying that this grammar is ambiguous. Okay, this grammar is ambiguous. Why this grammar is ambiguous? Because this I can give you some string, I can give you at least one string, I can give you actually many strings I can give you, which you can derive through A also, through B also. Okay. So now let's see this grammar, why this grammar is ambiguous. Let's see. Let me give you one example. For example, you consider AABB. Okay, let's consider for a moment, let's consider AABB. Okay, let's consider this. So you can see for this string, how many pass tree you can generate? You can see S can go to AB, then this B can go to SB, then this S can go to AB. Okay, yes or no? So what I got? I got AABB. Okay, yes or no? I got AABB. BB. Okay, so this string AABB I got. Now, what you can do? You can create another parse tree. What you can do? You can go to AB, then this A can go to AS, this S can go to AB. Okay, this also you can do. This S can go to AB. Now, again, you can see that what we got A B B. Okay, so definitely for this string we have more than one parse tree. Yes or no? For this string we have more than one parse tree. Okay, so definitely I can say this grammar is ambiguous. Okay, very simple. Now let's see the next option. The next option is saying GA is ambiguous. What is GA? GA, that is basically you are deleting A from this grammar, from this G, you are deleting A. So A is gone. The variable A is gone. Now what you got? You got AB or AB, B going to SB. Okay, this is what you got. Now the question is saying that GA is ambiguous. Is this GA ambiguous? This is actually not ambiguous. You can easily see either we will generate AB. If we go to AB, then this B will go to SB. And then again, either you can go to AB or you can go to AB. So basically, you can easily check actually this grammar will be unambiguous. Okay. This grammar will be unambiguous. Why this grammar is unambiguous? Let me tell you, because at any time, if you want to stop, at any time, if you want to stop the derivation, then you can use this production. And if you need more AB, if you don't want to stop the derivation, if you need more AB, then this will go to this will go to this. So basically, there is no ambiguity here. Okay, you can check it. Similarly, let me tell you this GB, which is grammar obtained by deleting the non-terminal B. What that will be? That will be AB or AB A going to AS. Actually, you can check this is also similarly, this is also unambiguous. This is also similarly unambiguous. Why this is unambiguous? Because at any time, if you want to stop the derivation, then you can use this production. But if you need more AB, then you can see that this S will go to here and this A will go to here. Basically, you can easily check some examples you can take and you can check that these are unambiguous grammars. I hope you understood. Now let's see the language. What about the language? So already the language of S, what that was? To find the language, you can apply the substitution, right? Okay, this I can also write as A S going to ASB or AB. Okay, you can apply the substitution. Here you can see. Here you can see S going to ASB or AB. Okay, this is duplicate production. So you can see S going to ASB or AB. So here you can see what will be the language, what will be LG. You can see from here you can find what will be the language. So LG, that is basically you can generate AB or you can generate A power n, B power n, S, and this S I can replace with AB. So it will be like A power n, B power n, where n is greater than equal to 1. Okay, this will be your language. Clear? This is LG. Now what is GA? First you find what is GA. We are deleting the non-terminal A. Okay, let's delete the non-terminal A. Then what you got? The non-terminal A we are deleting. Then you got this. Of course, this is equivalent to, you can apply the substitution rule, and this is equivalent to ASB or AB. Did you notice that this is equivalent to already this? So the language will be same. Yes or no? The LGA, that also will be A power n, B power n, and greater than equal to 1. Okay. Similarly, you can see this GB, you are deleting the non-terminal B. So what you will get? Deleting the non-terminal B. So what you will get? Here also you can see that this is equivalent to, you can apply the substitution rule. Whenever S will go to A will go to AS. So ASB or AB. Again, you can notice that this is actually equivalent to this is equivalent to this. So basically, the language of G, language of GA, language of GB, all these are basically same. And G is ambiguous, but GA, GB, these are not ambiguous. GA, GB, GA, GB, they are unambiguous, and G is ambiguous. GA, GB unambiguous, G ambiguous, and the languages are same for all these grammars. Okay, I hope you understood. Very simple. So this is a simple question. I hope you understood the analysis. Okay, so this is enough for this session. In this session, a lot of questions we have discussed. The complete analysis of all these questions, I hope you understood. All the complicated questions I have already taken in this session. So I hope you understood each and every question. From every question, I hope that your understanding of the concept has improved. Maybe you found maybe some misconception, maybe some better understanding of concepts, some complete analysis, something. I hope that you learned from every question. Okay, so thank you everyone. Please share your feedback. Please put a comment. Let me know your feedback. Okay, it will motivate me. I go through all the comments and I consider all your feedbacks. It motivates me. So please share your feedback. Okay, thank you everyone.